Welcome to HC18. The morning tutorial. Multicore programming, from threads to transactional memory.
Let me introduce the first session chair and speaker. This very interesting topic was proposed by him, and he organized the entire tutorial. He's an assistant professor at Stanford, and he's at the Computer Systems Laboratory. He received his PhD in computer science from UC Berkeley. Please welcome Christos Kozyrakis.
Good morning, everybody, and welcome to the morning tutorial. The title is Multicore Programming from Threads to Transactional Memory. So the motivation for this tutorial should be straightforward. In the past few months, we've had every single major processor vendor introduce multicore chips, and that includes all application domains, server, desktop, and even embedded. So that brings up the natural question, how do we write software that can efficiently exploit multiple cores? In some application scenarios, all you have to do is multiplex requests from multiple users or multiple clients, but that will take you that far. Eventually, to accelerate one program, one task, one request, you have to figure out how to do parallel programming. So here's what we're going to do today. We're going to start by talking about multithreaded programming, which may not be the only way to write a program for a multicore chip, but it's a very commonly used technique in the industry. So we're going to go over the models, the tools, and the challenges that you would face today if you were to do multi-threaded programming. And then we're going to switch gear and look a little bit into the future and talk about transactional memory, which is a technique currently in research that promises to greatly simplify the way that we do multi-threaded programming. So we're going to have an overview of transactional memory. We're going to talk about some example uses. And of course, we're going to talk about what it will take to implement this technique. There are 4 presenters for this tutorial, and I'm going to introduce them in the order of appearance. And in one way or another, we're all experts in either multi-threading or transactional memory. So the first presenter is Yuan Lin from Sun Microsystems, where he is a senior staff engineer in the Scalable Systems group. He has extensive experience in compilers and tools for multi-thread applications, and he is a member of the OpenMP specification group. The second speaker is Ali-Reza Adl-Tabatabai from Intel, where he is a principal engineer with the Programming Systems Lab. And he's working on compilers and runtimes for future Linder architectures, including support for multi-threading and transactional memory. The third speaker is myself. As you heard, I'm an assistant professor in Stanford in electrical engineering and computer science. The past 3 years or so, I've been working on programming models and hardware support for transactional memory. And then the last speaker is Bratin Saha, also from Intel, the Programming Systems Lab, where he's a senior staff researcher. And he's working on the design of highly scalable runtimes for multi-core processors, and he's also looking into support for multi-threading and transactional memory. So here is our agenda for today. We're going to spend the first half, more or less, of the tutorial on multi-threaded programming. Then we're going to take a break, and then we're going to switch into transactional memory, and we're going to break this down into 4 parts: introduction, overview of implementation techniques, hardware transactional memory, and then software transactional memory. So a few reminders before we start. First of all, save your questions until the end of the corresponding part or until a speaker tells you that we're going to take a break now for questions. That will help the flow of the tutorial. So you will have at least 4 or 5 chances to ask questions throughout the tutorial. And of course, there's going to be a big Q&A session at the end. So there will be plenty of chances for that. We have an extended bibliography attached to the end of the handout. So you can see the papers that give you the details of what we're going to talk about. And then before we start, I'd like to ask you all to first turn off your cell phones so we don't necessarily interrupt the tutorial. And then as it turns out, it's a bad idea to touch the bag in which the proceedings came in. So get your handout out and leave that bag alone. So with that, I want to turn it over to Yuan, who's going to start with a discussion of multithreaded programming.
Okay, let's start. Any tutorial should start with a survey. So how many here of you think you're software engineer or software developers? Okay, how many think yourself a hardware engineer or hardware developers? Okay, about 1 to 2. Okay, so let's start. Doesn't work. Okay. So I just want to set the stage that what's the multi-core architecture I'm going to base on. So there's many different kinds of implementations. But generally speaking, it's a chip, contains multiple cores, and on each core, there are multiple hardware threads, or we call threads. So different cores or chips may share cache at different levels. All the hardware threads access to the same shared memory. So Christos just illustrate some ideas why we are going in this direction. There's a bunch of reasons, and I guess you all know that. This slide shows some typical number of cores and number of threads on each core. So we're coming from, where is that? Like you have one chip, there's only one core, and on each core there are 2 hardware threads, like Intel's Pentium 4 with hyper-threading, or go all the way to Sun's UltraSpark T1. You can have total 32 hardware threads on a single chip. So just an update. The slides I'm showing here is updated version. It's newer than the version that you have in your handout. So please look, heads up and look at the stuff on the screen instead of go through your handout. I was told that the updated material will be available on the CD once delivered later. So this gives you a brief idea of the 32 hardware threads chip. But the most important thing is that the OS, from a programmer's point of view, the OS sees each hardware thread as a processor, and OS schedules the threads on the hardware thread, and the hardware schedules the hardware threads in each core. So we have this thing, right? So I know this is a tutorial, but I'm going to say something controversial. Anyway, I know it's recorded. So what's going on here in this industry? The hardware guys, my view is the hardware guys just threw the problem over the wall. They used to give us high frequency. Now they cannot go there anywhere. So they say, oh, I have this wonderful, I have multi-cores. But how do you use that? Throw the problem over the wall. Software guys take care of it. And now we're going to have transaction memory. Wonderful idea. How do I use it? No, we don't know. Throw it over the wall. So software guys, oh, the panic, say, free lunch is over. What should we do? So the question is, how can we use these multi-core architectures? How can we use these transaction memories? So we look at the applications that are outside there, the different kinds of applications. Some are called multi-processing applications. So they are well fitted for the multi-core architecture. And some applications are multi-threaded already, like CBL, CIM. They are well suited for multi-core architectures. But there are still a bunch of single-threaded applications. So what should we do with those things? They cannot benefit directly from the multi-core architectures. They either have to go multi-processes or multi-threaded. So are we ready? So means are the developers ready? There's the language developers, there's compiler tools developers, and OS developers, runtime developers, virtual machine developers. Are they ready? So what are the challenges? So those are the questions that I'm trying to address today. So this is a brief overview of the topics I'm going to talk today. The first is the overview of the multi-core architectures. I've done that. Then I'm just going to briefly talk about the 3 commonly used language APIs to write multi-threaded applications. Then I will go through all the challenges. So first, I will talk about these 3 languages. So if you're going to write a multi-threaded application, there are different programming models. So these are the 3 most popular programming models: the shared memory model, a global address space model, or message passing model. So in the shared memory model, memory is shared unless it is declared by the programmer. It's private. So you can access the shared memory by direct read and write. So the most popular, this is the most popular approach on the multi-thread application architectures. So they use examples like pthreads using this programming model, OpenMP, Java, and the C#. So it's more close to the multi-core architecture than the rest of three. So the other is global address-based programming model, and the other is message passing model. So I'm going to talk about these three. So how many of you have written pthread applications before? OK, cool. How many are using OpenMP? Oh, just as expected. And how many using Java? Less than expected. OK. OK, so pthreads. So the pthreads, most of the specification of pthreads is defined in this spec, and they have a lot of stuff like how you create threads, how you terminate threads. You can do synchronization, schedulings, interaction between threads and the processes, and data management. All those things is defined in this spec. And over the years, gradually, more stuff are put into it. And the latest development is that all the specification is merged into a single Unix specification v3 and a new set of synchronizations primitives are added into the spec, like barriers, spin locks, and read-write locks. So I just used this as an example to show some flavor of how you use pthread to write programs. So we're doing a very simple thing. We're doing there's compute is a function call. They can be executed concurrently. You compute 1, compute 2, and get the result, and do addition, and save the result to G. So how do I do this in pthreads? So basically, you will create a thread using pthread call, and this will give you the thread ID. So this is the property of the threads, and you give the entry function of the routine that the thread is going to execute, and you pass an argument for this routine. So create the threads. So this thread 1, you go here and create threads, becomes thread 2. The thread 2 will work on work. Itself will go ahead and work on work. So when it's done, we do a join. OK? So this is how the work looks like. So it's take the argument, do compute, get the result. And because both threads are working on the global variable G, we put into a mutex lock, so I get the result of G. So that's the idea. That's how you write a pthread application. So now here's a little quiz. So we'll try to understand what concurrency is. So question. So what happens? What is the status of thread 2 at this point when the first thread returns from pthread create? So is thread 2 waiting, has not started working on the function work, or thread 2 is executing work, or it has already done work and returned from work? So what's the status of thread 2 at this point? Answer could be any of the three. That's concurrency. So you don't know. So the beauty of threads, pthreads, it's kind of has long history and has a pretty comprehensive set of functions and APIs. You can use to build more high-level synchronization libraries. So that's pthreads. Next, OpenMP. So what is OpenMP? OpenMP is, somebody calls it a language. It is not. It's basically an API specifications for writing shared memory programs in C, C++, and Fortran. So it consists three major parts. One is compiler directives. Tells compiler how to translate code into parallel version. And the runtime routines, like lock routines. And a bunch of environmental variables tell the thread's behavior at runtime. So this is the URL. You can go ahead and find the specification. Right now, the specification is at 2.5. And the language committee are working on 3.0, try to bring more features into OpenMP. So OpenMP have a very specific execution model. Basically, fork and join. So you have a thread called master thread. It enters a parallel region. It will fork a bunch of slave threads, then execute this parallel region. After the parallel region, conceptually, all the threads will join and go to the next parallel region. So we go back to the same simple example. So how do I write this code in a sequential code? This is where you will write it. So for OpenMP, what you do, just add a pragma. Tell the compiler, say this is a parallel loop. Each thread is just execute one iteration of this loop, and I'm doing a reduction on G. The compiler will take care of it. So the beauty of OpenMP is it's possible to write a sequentially program that and is functionally equivalent to its parallel version in the same code. And this makes debugging and incremental parallelization extremely easy. What you usually do is that you can have a compiler, ask the compiler to ignore this pragma and debug your code, the sequential version, and debug, find all the problems you will encounter in the sequential version. Then you add a pragma and turn it into the parallel version and only care about the bugs that appears in the parallel version. So Java has some basic threading support in the original spec. It has how you create threads. It has condition variables. I structured the synchronization blocks. Most recently, in the Java J2SE5, two major improvements. The first one is the specification of the memory model. The other is add a bunch of concurrency packages. It introduced a lot of easy-to-use, high-level utilities the user can go ahead and use. So this is a Java example. It gives you same, illustrate how to use Java to handle the same code. You can do a thread create and thread join, and you implement a class that has a runnable interface. This is the message will run when you start the code. And I use a automatic variable to get 1 and 2. And you can use a synchronized block to do the reduction on G. So this gives you a flavor of Java. So the beauty of Java is it's well-defined and well-specified on the memory model. It has a set of easy-to-use and reliable and high-performance concurrency utility that can help you to make the program easier. So that's it. So that's the overview of the language. Now we go into the detailed challenges. So I have this language, right? So nobody can expect to give you a language specification and become an expert program. There's real challenges in the real life. So what are challenges? I work with the Intel guys and the other authors for this presentation. We come up with 11 challenges. So the first one is how do you find and creating concurrent tasks? How do you map tasks to threads? How do you define and implement communication protocols? How do you deal with race conditions? How do you deal with deadlocks? You have to deal with memory models. How do you compose parallel tasks? And how do you achieve scalability? And how do you achieve performance? And the performance is predictable and portable. And how do you recover from errors? And you still have to deal with all the single-threaded issues. So this is the overview flow for each of the challenges. I'm going to talk about what it is and how do programmers deal with it right now, and how does the language, does any help from the language, and if there's any tools can help. This is just a brief flow. So let's start with the first one. So how do you find and create concurrent tasks? So there are two kinds of concurrent tasks. One is called data level concurrency. So you can have 6 crying babies waiting for diaper changes. So I've been through this recently, so I use this example. Not 6. And the other is concurrency at a functional level. You can change the diaper for the baby, use your hands, and you can complain to your spouse, ow, and you can play something in your mind, assuming that all these function units are not reused for different tasks. So you have to deal with the granularity, whether you want to create tasks as big or small. The bigger you have, the less concurrency you have. The smaller we have, the more concurrency you have, but you have to deal with all those concurrencies. So it's tough. So do the trade-off here. So I don't think there's any way that any tools available can help you to find the concurrency. It's really in the programmer's mind. They have to design it. But there are certain ways people have been trying to help. The first one is automatic parallelization. So it's a long history. It's available in compilers. The idea is you write a sequential program, the compiler will figure out the concurrency and do smart things for you. It's available in SGI, Sun, IBM, Intel, those compilers. Here I just use a Sun compiler, Fortran 90. You give this specification, the flag, say X autopar, compiler go and figure that out. Long history, mostly loop-based, limited in scope of success. I'm not very optimistic about this right now, but people are still pushing it. We hope that one day there will be a breakthrough. So if compiler cannot do this a wonderful job, perfect job, there's any tools can help. And also there's this example that we call parallelization assistant tools. So it's semi-automatic. This example is, the tool is called Parallelwise. It's from this company, Parallel Software Products. It also has a long history. People try to do this. They try to figure out, oh, if I cannot find this variable to be private, what's wrong? Can user tell me any information about the program? I can do something smart. But still, there's a limited adoption. So this slide shows a very interesting thing that I talked with one customer says, oh, we're trying to help you to parallelize the code. What's the most wonderful tool you want? This gentleman is from Aachen University. He said, sometimes you don't need to be very fancy. You just tell me all the global variables in my program and show all the places this global variable is accessed and show it in different color. That's a wonderful tool because I can go there and I decide whether it will make my program thread unsafe and whether I want to try to privatize it. So that's some idea. So for the language, pthreads, there's no direct support. You cannot, the language cannot help you to find and create concurrent tasks. Java, also no direct support. But if you use the executor or thread pool, then the concept of tasks, it will force you to think in terms of tasks. For OpenMP, it doesn't help you to find the concurrent tasks, but it has some pragmas constructs for you, makes it easier to specify tasks. For example, if you want to do loop level parallelism, you can say OMP4. If you want to do functional level, you can say use sections. So each one will create a task. Okay, so we also have this task, and we want to map the task to threads. So in early days, when we have threads, people say, oh, threads are wonderful. I just assign a thread for each task. Done. But it's not scalable because the system cannot provide the number of threads you wanted. For example, you can have 1,000 threads if you have a game server, you have a web service, there's tons of requests, thousands of them. So if you do this, then the system may not be able to provide the threads you want. What happened? Your program is not scalable. And there's also overheads associated with creating threads, destroying threads. So what people usually do now these days is to sync in tasks and create threads and map tasks to threads. So you want to use a well-defined data structure to hold the task state, and you can deploy a thread-to-task model to achieve scalable and predictable performance. You can do a master-slave model. You can have a master threads. You can dispatch slave threads and assign the tasks to all those slave threads. Or you can use a pipeline, and each thread performs specific operations on data item and pass the data to the next one in the pipeline. Or you can use a task pool model. Basically, each thread go ahead and execute something, and during the execution, it finds more tasks and put tasks in the pool, and next threads come in and execute tasks from the pool. So for pthreads, there's no direct support. For OpenMP, it's using the basic master and the slave model. So master come here, creates a bunch of worker threads, and the master will decide what kind of scheme you use for the whole team to get the tasks to work. For example, that you can, for loop level parallelism, here's an example. You can have 16 iterations. Each iteration can be considered as a task. So you have 4 threads. So you want to define how you map these iterations to those threads. So you can use a static scheduling. In this case, each thread just go ahead and grab 2 iterations. 2 iterations and work on it, then roll back and get another 2 iterations to work on it. This may not achieve the load balancing you want if all the iterations, the granularity for the iterations are different. So you want to go dynamic scheduling. So all threads go there and find iterations and get the first iterations it can execute. Or you can use a guided scheduling. So all the work assigned to the threads are in the exponentially decreasing order. So for Java, you can have the thread pool utility, and it has built-in mechanisms for you to assign the threads to a bounded number of a task to a bounded number of threads. So this shows an example here. So you can create a task pool, then you can create a threads pool, and then create a task. So the task is going to accept a socket. This is a web service example that accepts a socket and deal with it. So you can create thread pool. Then you can create new tasks. All the tasks are generated sequentially, but the task will be put into the pool to execute concurrently. Okay. So the third challenge is to define and implement synchronizations. You got to need to understand the application logic and design the high-level synchronization schemes. For example, you can have a traffic light. This is the high-level synchronization scheme you have in your program logic. But you have to map that using the lower-level synchronization primitives you have in your program. For example, you want to execute all your threads in phases. You want to coordinate all the threads in the phases. So there are different schemes you can use. You can use condition variables. So all threads coming to a wait on a something to happen. Then another thread comes in when the condition is satisfied. It will signal or broadcast the information to all the threads so they can go on. Or you can use barriers, so make the threads to go lockstep. Or you can simply create and join and create new threads if you want to do that. Each one has its pros and cons. You want to look at your application logic to pick the one that's most appropriate. So for synchronizations, the pthreads provides mutex locks, condition variables, semaphores, barriers, read-write locks. OpenMP provides something, logs, barriers, critical sections, ordered regions. For Java, they have all a set of logs. All those things are pretty low level. You want to really map them to the logic that you have in your program. Okay. So the fourth challenge is race conditions. This is almost the most tough problem you will find in writing multi-thread applications. So race conditions occurs when different threads access the shared data without explicit synchronizations. So race conditions can cause your program to behave in the ways that are unexpected, so make the program extremely difficult to debug. Here's an example showing a race condition. So assuming I have two variables, A and B, the initial value of A and B are 0. So for thread 1, you add 5 to A and add 10 to B. And in thread 2, you minus 10 from B and the -5 from A. Then you put the operation on B in log, but you do not put operation on A in logs. So what will happen? What's the value of A and B after the barrier? Depends on how the threads are scheduled. So if the code is scheduled this way, happens to be the log in thread 1 happens before the log in thread 2. In this case, this guy, A will be 5, 10, B will be 10. Come here, B will be 0, and A will be 0. So the result is A is 0, B is 0. So if the threads are scheduled the other way, what will happen? Because you put this in log, come here, B will be -10 here, and you +10, it will be 0 again. But what's the value of A? It really depends how this get scheduled. The value of A can be 0, can be 5, can be -5. So there's a race condition here. Makes your program, the result of your program, undeterministic. So there's two kinds of race conditions, essentially, in your program. One is data race. The data race happens when the two threads concurrently access the same memory location. At least one is a write, without protecting the access by critical sections. In this case, the atomicity of the access is lost. For example, you have two accounts. You want to do a transfer between these two accounts. You really want to put these two access in logs or critical sections, or use some scheme to make sure the atomicity is achieved. There's another kind of race is called a general race. So the general race is the order of the access to the shared memory is not enforced. So in this case, you can have two threads working on jobs from a queue. So for thread 1, you put the job in the queue. Then you post the information, say, I'm done. I have a job in the queue. And the thread 2 just wait and get job from the queue. If you don't do this, if you don't have a post and wait synchronizations, then you will have a race. So conceptually, a data race is also a general race. A data race can be fixed by using critical sections or adding synchronizations. A general race can be fixed by adding synchronizations to enforcing orders between different operations. So you need to watch out for general race when the shared memory access should happen in a specific order. You want it to happen in a specific order. You need to watch for whether my program has general race. If your program can allow some asynchronous behavior, then you should watch out for data race. So there are tools available. The tools can be used to detect data races, but I'm not aware of any tools that can help you to detect general races. So the tools that can detect data races, there are different kinds of tools. Generally speaking, there are two kinds. One is the static analysis tools, and there's runtime analysis tools. So the static analysis tools can be fast, and they can consume little memory. The beauty of it does not affect the behavior of your program because the static analysis the detection is not happening at runtime, so it has no side effects to your program. It's not affected by input data or scheduling. It can be used by the OS or the drivers. But the problem is because it doesn't know the whole picture of your program, and because of the limitation of static analysis, it may generate some false positives. So a typical example of static analysis tools is the log-linked from Sun. So the history is log-linked like this. Sun is going multi-thread big time in early days, and we have Solaris. We have deadlocks in Solaris kernels. So somebody go ahead and write a tool called Warlock to detect data race in Solaris kernels and device drivers. And the management team said, oh, this is a wonderful idea. So they rewrite it and make it a public available product called the log-linked. It's available now. You can use it to detect deadlocks and data races. Oops. So another class of detection tools is runtime detection. So I listed here that are available today, mostly a commercial products, not including research work. Hilgran from Wilgran, so it's available on x86 platform. It's open source tool, and HP Visual Threads, Intel Thread Checker, and the Sun has data race detection tool, which is in alpha state now. So this screen shows the Sun's race detection tool, basically to find all the races in your program. It shows whether the read or write and the line number where the race happens, and can give you a call stacks. So once you have a data race, we have these tools. What should you do after data race is found? So that's the question. It's even more important than how you find data race. So you need to check whether it's a false positive, because no tool is perfect. A false positive is reported data race, but actually does not exist in your program because of the limitation of your tool. For example, the tool may not understand all the synchronizations user put in your program. In the program, because of synchronization, user put there the code execute in certain order, specified fixed order, but the tool doesn't understand it. They say, oh, they may execute it concurrently, so it will report data race. Okay? If you verified it's not false positives, you want to make sure whether it's a benign race. So what is benign race? Benign race is some race that the program put in the program. It thinks that if I allow some races, my program may execute faster. We'll see some cases later. But are you sure? Is the intention of the programmer? Is there an error? You need to check and double check again. And the programs with intentional data races are very difficult to get right. So are you relying on the sequential memory model? Are you making any assumptions? So you need to double check. So once you identified, oh, this is not a false positive, this is not a benign race, this is a race, it's a real race. So how do you fix it? A race is not a bug in your program. Race is a behavior that's exhibited in your program. It can be itself could be a bug, or it could be caused by a bug in your program. So you need to fix the bug, not the data race. So I show an example here. So you have a pthread. This is protocol of interface of pthread create. Notice that you can give a start function for each thread, and it also can pass argument for each thread. So here that I want to create a bunch of threads using this call, and for each work routine, I want to give the iteration ID as the argument. So because this argument the type is a pointer to void, so in this program, the programmer thinks, OK, I just pass the address of I to this routine, and here I cast it to point it to int, then get the contents of this address, so I can get I and work in this routine. So if you run this, with report data race, the two-word report data race. Why? It thinks that there will be a race between the read of this data and the write of this data. How come? Because the reason is because you pass the address of I, right? So you pass the address of I. So one thread go ahead and access I. It finds when you do this, this thread may go on to the next iteration. The value of I may be changed. So it could that two threads will find this value to be 2. So in this case, there is a data race. So the problem is here. The bug is here. The race is here. So if you find, oh, I have a data race, I just put this into a critical sections. I fixed the race, but I didn't fix the bug. And most tools can detect certain kinds of data race. So you really need to fix the way that's really safe. For example, here, this is another example. You have two accounts. So you want to do a money transfer between these two accounts. Thread 1 does one operation, thread 2 does one operation, and have thread 3 try to check the account. So the premise is that the two accounts should be balanced. The sum of account 1 and account 2 should be a constant. But if you write code in this way, the accounts are not balanced because the data race in this code. So you can fix it. So this is one way to fix it. You can put all the access in logs. So if you do this, most tools will go there and find there's no data race because all the access are protected by logs. But the accounts still not balanced because the order between all these operations is still not defined. So the tool cannot, if you run code in this way, the tool will not tell you there's a data race. You fix the data race, but didn't fix the problem. The right fix is you want to put these two operations in one critical section. So this is the right fix. So the intelligence of fixing the problem is still in your hands. You cannot rely on this tool. The tool just tells you a behavior that's exposed in your program. And once you fix the bug, you want to run the tool again and again. And you give different input sets because your fix may introduce extra data race, or you want to try with a different input set because different runs may expose different data races. So once you find data races, you want to put them into critical sections. But there's another way to fix that. You can make the shared variable to be thread private. So there are different ways to make global variables to be private. For pthread, you can create thread-specific data using these APIs. For OpenMPs, you can add the thread private directive to make variable private. For Java, they also introduce a thread local class. And also, there's a runtime linker and a compiler features you can use in most operating systems. You can specify a variable to be thread, and they will use thread local storage. And you also need to watch out for the routines that you call, function and the library routines and OS routines, whether they are empty safe or not. There are 4 different levels of empty safe. The first one is unsafe. Basically, these routines, they contain some global variables, so they're not empty safe. So you want to use the empty safe version. So it's safe. The second category is safe. So the implementer of these routines, they will put logs. They're protected. But you can get empty safe feature of these routines, but they may not give you the concurrency you want because maybe the odd entry of this routine is protected by a single lock. So you can get safe, but you cannot get concurrency. The third class is empty safe. You can get empty safe, and you get a reasonable amount of concurrency. So the fourth level is async safe. Basically, these routines can be called in a function that in a asynchronous signal handler. So the code will not be deadlocked. OK, so the fifth challenge is deadlock. So the deadlock happens when 2 or more competing actions are waiting for the other to finish, but no one can proceed. So a common misunderstanding is that deadlocks must involve locks. This is not true. Deadlocks can be caused by synchronization, incorrect use of synchronizations, like barriers. Another phenomenon that's similar to deadlock is life lock. It's just like 2 people in the corridor try to give way to the others. They keep changing positions, but no one can proceed. So this is like a classical textbook slide, give you the 4 conditions for a deadlock. So you need to have a mutual exclusion. You must have a code and a wait, and no threads, only the process holding a resource can release it. So no preemption. And all the weights and the holes must form a circular weight. So if you have these 4 conditions, then those are necessary conditions for lock to exist. Once you have deadlocks, there's 2 ways. You can prevent the deadlock from happening, or you can avoid a deadlock from happening. You can use protocols to ensure at least one of the 4 necessary conditions does not hold. For example, you can enforce a lock hierarchy to ensure that there's no circular weight. So you break one condition so you can prevent the deadlock from happening. Or you can use global resource information to decide a request should be granted or should be rejected or delayed. So a textbook example is Banker's algorithm. You can use that to avoid deadlocks. So it's made easier to look at this in the textbook context when the deadlocks involve some resource. But in real code, it's not obvious, especially when deadlocks are caused by synchronizations. So you want to always examine the program logic. So in the next few slides, I want to show you some examples, really simple examples of deadlocks. The first one is the typical one. You have locks. Thread 1 try to lock variable A, then try to lock variable B. And thread 2 do B first, then C, and thread 3 does C and A. So there forms a circular weight. There's deadlock. But the program may or may not deadlock in a particular run. So a tool needs to detect, even if there's no deadlock in a particular run, but there's potential deadlock, a good tool needs to detect that. Example 2. This does not involve any explicit locks. What happens is thread 1 tries to join thread 2, and thread 2 tries to join thread 1. In this case, nobody can finish their work. And these 2 operations, none can be finished successfully, so there's a deadlock. Example 3. This is OpenMP code. You can create a parallel region with a team of 4 threads. This function call returns the ID of the thread. So it says, if the ID is less than 3, I wait on this barrier. If the ID is greater or equal to threads, I wait on this barrier. Because of 4 threads, and you put each barrier expecting 4 threads to reach the barrier, in this case, there's deadlock. So OpenMP makes this kind of scenario illegal. But this seems really happen in user code. The last example is kind of interesting. What the programmer does here is that he has a global variable called flag. So the initial value of flags is 0. So thread 1 here tries to wait until the flag set to non-zero, and then exit. The thread 2 here set the flag to 1, then try to join thread 1. When you run this code, you may very likely get into a deadlock. You will find that you have an infinite loop here. So what happens? Compiler can do something under the hood. What happens is that the compiler can do a register allocation and turn this while loop into the form like this. It can read the flag only once, put into register, and do testing here. Then if it happens that the flag value is 0, then this will be an infinite loop. So you will get into a deadlock here. So once you program hands, you see, oh, I have deadlock. But you really need to look into the reason why it's deadlock. This is not easy, and there's almost no tool. A single tool can help you. In this case, what you do is just you run in a debugger and stop the program, look at the stack trace, look at the assembly code, figure out what's going on. So for deadlocks, how the language helps. the pthreads, there's no direct support for it to detect deadlocks, but there are some error checkings on lock errors. For OpenMP, there are also some checkings to make sure deadlock illegal. Some kind of deadlock is illegal. So you can have tools to detect that. For Java, Java has a structured synchronized method of block, which makes a critical section easier and cleaner than unstructured blocks, unstructured locks. So it makes you easier to reason what's going on. And the locks associated with synchronized keywords are always released when the threads leave the scope. They will do it automatically for you. This is a plus and minus. The minus side is that if there is an exception when the error happens and the thread may leave the synchronized block and will not protect the block with locks, so you will have a state that's inconsistent but is not protected by locks. So there's tools to detect deadlocks. There's static checking locks like locked from Sun, or runtime checking tools like the thread checker from Intel, or like for OpenMP specification errors, Sun provides a OpenMP runtime detection embedded in the runtime library of OpenMP runtime libraries. So for example, you can set the environment variable, turn the Sun WMP1 to true, and run it out. If it's OpenMP program and you have two different members of thread team at different barriers, the runtime library will give you an error. So the fifth challenge is to deal with memory consistency. So memory consistency specifies the order in which memory operations will appear to be executed to a programmer. There are many things will affect the memory consistency. The language affected, the tools, the compiler, the runtime, and hardware. They will all define, together will define and give you the final memory consistent model you will have. So here I use an example, the famous lazy initialization example here to illustrate the idea. So basically, here is that you have a data structure type of A, and you want to create only one singleton of this type in your program. So you put into a routine and makes this singleton a static variable. So in the sequential version, you will write this way. You come here, you check whether the initial value of single A is null. If it's not null, just return this value. If it's null, you will do a malloc, get the memory space for this singleton, and assign value to this pointer, and return this pointer. This is easy to understand, but does not work in multi-threaded applications. So this is one version that you can make it work to make it empty safe. You come here, you do the checking, you do the malloc, you do the assignment, you put all this into a lock. So it works. The problem with this is not very, it's not efficient in some cases, especially once the variable is already initialized. You have to do a lock every time. So this is kind of smart way to fix this. So it's called double checking. So you come here, you assign the value of single A to a temp variable, local variable, then you check the variable without doing any lock. If the value of single A is not null, you return temp. It's already been initialized. If it's not being initialized, then you do a lock. Then inside this block, you check again, because between this check and the lock, another thread may come in and modify the value of single A. So you really want to check again. So put this in the lock, you check, then you do allocate memory, you do assignment to, you fill the data in this data structure, then you assign the value to single A, then you do unlock. But this model may be broken. It's called a double-checked locking. So what happens is that you look at these two statements, right, within this critical region. The compiler may reorder these two operations. You don't know, the compiler may reorder this. Even the compiler do not reorder this, the hardware may reorder this. So if these two statements are reordered, what happens? If another thread comes here and call this routine, get the value of P, then try to access the value of P. If these two are reordered, then the value of data 1 and all the other data may not be initialized at this stage. Even P is initialized. So your program may crash. So there's one possible fix is you can add a memory barrier between those statements, make sure the compiler does not reorder them, make sure the hardware does not reorder them. But it may still be broken on certain architectures. So this is the almost another very difficult problem in writing multi-thread applications. The problem is, first, it's difficult to understand, to reason with it. The second reason is that there's almost no specification, a good specification in the language you write. For example, in pthreads, there's no formal specifications. The only thing says in pthreads that for any shared memory access, you must be protected by pthread API calls. So in the previous example, the two threads will try to access the same memory location, but there's no pthread API calls. So based on pthreads, your program is broken. It's not guaranteed to work. You cannot reason with it. And for C and C++, the specification assumes single-threaded execution. There's no concept of multi-threaded. There's no concept of memory model. And right now, the C++ language committee is working on specifying the language model. Until then, it's still very tricky to get it right. So for OpenMP, it's better. The committee has studied this problem extensively. So now there is a detailed called clarification, but still no formal specification. The idea is that each thread has a temporary view of the shared memory. Then a flash operation is used to make sure the thread's temporary view is consistent with the global view of the shared memory. And all threads must observe any two flash operations with overlapping memory space in the sequential order. So far, the most well-defined memory consistent model is Java among the three. It's being revised and clarified in the JSR 133 efforts. So basically, it tries to define a certain, for each, so for certain events, it will specify a happen before ordering. So two threads working on some memory, if the memory access is not enforced by this happen before operations, then there will be a race. So it is well specified when a race can happen. So it will define operations on volatile variables, final variables, and immutable objects, and a bunch of APIs. It specifies the order when this should happen, which will happen before the other. So, but the general lesson is that try to avoid writing programs that have deliberately have data races. It's very tricky to understand and to debug. So the seventh challenge is how you compose parallel tasks. So it's easier than when you can write one parallel region, you have parallelize one particular module. But modular design is common in software programming, right? So you really want to have each module can be parallelized, we can run in concurrently. But the difficulty is that how you compose them together to get a reasonable performance and make sure it works, doesn't have problems. So there are three models of composition. The first one is sequential composition. The idea basically is that you just make sure one execute after the other. For example, we'll have two functions, F1 and F2, each one multi-threaded. So A, B, C are the input data and output data. So just make sure one happen after the other and take the input from the other. So if you have, you want to create n threads, then you use n threads for F1 and use n threads for F2. So this is the most simple form of composition. Or you can do a parallel composition. The idea is similar to a pipeline. So you have F1 and F2, and assuming they are not overlapping in the functions, so you can create n1 threads for F1 and n2 threads for F2. They still have n threads, but they work in a pipeline fashion. So if you do this, the benefits, you may improve resource utilizations by overlapping F1 and F2. But disadvantage is that you may introduce extra communications, like data migrations or thread migrations. The third way is nested composition. So this is the form that most people have in mind. You can create n1 threads for the F2 and the n2 threads for F2. Then totally you will have n1 by n2 threads in your program. So the straightforward approach is that the outer module and inner module just create their own threads. So I don't care about whether my context is. I only know my word. I'm going to create the threads I want. So the problem with this is that you may have thread explosion. You don't know how many instances of myself will be running. So just go ahead and create threads. A more complete approach is that outer module and inner module will get threads from the same thread pool. So then you need a common thread framework. So different modules need to communicate with each other. What does that mean? That means either you need to change your APIs, you pass information through the APIs, or you have to maintain some extra states so the modules can query. And if you're trying to use logs, you should be watch very carefully because logs are not composable. You may run into deadlocks. So any help from the language? For Python and Java, there's no help directly, but you can do smart things. For OpenMP, it's specified in the language. So you can support nested composition of parallel tasks using nested parallel regions. So for example, here you have 2 for loops. Each one can be executed in parallel. So you just can say OpenMP parallel 4, OpenMP parallel 4. This is a well-specified behavior in OpenMP specification, and the compiler the runtime and take care of it. But the problem with nesting tasks through nested parallel region is it's inflexible and may result in poor utilization of resources. So the eighth challenge is to try to achieve scalability. So what's scalability? What's the scalability problem is the performance does not scale with the number of threads used. So there's a couple of reasons. The first common reason is that the system, you oversubscribe the system. The system can only provide 16 hardware threads, but you try to create 32 threads, 128 threads, you don't know. So the system will be oversubscribed. So the more threads you create does not give you more high performance or high throughput you want. Or the program you have does not have enough concurrency, MDAS law. So number 3, you may have lock contentions. So you have too many locks, too many instances of trying to acquire the same locks. And a single lock may hold too long, so you may have lock contentions. This is another common reason. So here's a tool that's provided in Sun Solaris called the plock status check. It will help you to detect user-level lock operations. So it's based on the very powerful dtrace. It's based on the dtrace plock STAT provider. So it can give you 3 types of lock events. Lock contention events, lock holding events, or error events. So the dtrace will instrument the code and provide information of these 3 events. So this giving an example. You can have A out, then you can say plock stat on A out. So what happens in the OS, when you try to lock a variable, the OS will check whether it's already being locked. If it's not locked, the lock is granted. If it's not locked, the OS tries to figure out who is holding the lock. Is the holder is running? If the holder is running, I will spin for a while, assuming the holder, because it's running, it may finish its work and give the lock to the one requested. If the holder is not running, I will block. So the first information the plock STT gave you is mutex lock. Mutex lock is blocked. So this gives you the caller of the lock routine, and this gives you the symbol of the lock variables, and this gives you the number of this event happens, and this is average time this thing happens. So this gives you, for 863 times that people call this routine try to lock this variable, but because the holder is not running, the OS say, I will block. So look at this, you'll see, this lock variable and this lock variable are causing most of the lock contentions. Okay, so here, same thing, that the OS tried to, this guy tried to lock these variables, but because the lock is not available, but this time the holder is running on the other processor. So the OS says, I will spin for a while, the same thing. And here is the number of times, even if you spin, you cannot get the locks, so I have to block. So it's a successful spin. So it gives you who are doing the contention. So look at this. These are 2 that's causing the problem. So look carefully. One is the mutex lock happening in the user code. The other is manlock lock happening in libc. It's a system library. So what's happening? So you can reason with it. Okay, maybe this guy, am I using the same, the correct manlock library? The default manlock in libc is safe, but it does not give you enough concurrency. The first thing the library does is lock itself, then do memory allocations. You really want to use empty malloc or uman to give you concurrency, enough concurrency, and empty safe. So for the user level lock, you look at, whether I want to resize my critical regions to make the region smaller, to make the holder time shorter, or you want to replace critical sections with atomic operations. So the good news is that there are certain kind of atomic operation already provided by the OS or by package from third party, like HP. They provide a atomic ops package, so you can use to do certain kind of atomic operations instead of creating a critical sections or using locks explicitly. And on Solaris 10, also a bunch of atomic operations are provided. And on OpenMP, there's atomic directive, so you want to increment the value of A atomically, you just say this. And for Java, same thing happens. There's an atomic class you can use. So another challenge is how to get predictable and scalable performance. So the idea is that I have written this program. I want to use the same program on different platforms, so achieve the same performance. So the performance, in the ideal world, the performance is only determined by the algorithm I used. It is not determined by something else. But in the real world, it's not. It is determined by the algorithm you used, but also determined by the compiler you use, also determined by the runtime, by the library, and by OS you use, and by the hardware you use. So it's not an easy job. So in order to achieve portable and predictable performance, you have to use tools to find where the performance bottlenecks is. What's the difference? So there's several available performance analysis tools. Sun has, Intel has, Quest Software has JProb for Java, and the Borland has tools for Java, and a bunch of other companies are providing this. And there's also OS-level tools you can use. So here I use Sun Studio Performance Analyzer as an example. So it's a general-purpose application-level profiler. So when I ask my team, say, oh, do you do anything specific for multi-threading? They look at me and say, what? It's a given. You have to do it because the OS is multi-threaded, and we are supporting multi-threaded applications. We are not tailored for multi-threaded. It's a no-brainer. Of course, it's multi-threaded, support multi-threading. So they say, oh, you have to use MT aware instead of say support multi-threading because it seems it's a shame for them to say we support multi-thread. It's a natural. We don't have to say it. It's insulting for them to say that. It does clock profiling, hardware counter profiling, and it also supports OpenMP. So what does this mean? I will say later. So this gives you a view of the performance analyzer. So this is a Java application, but we're not looking, it's a single-threaded Java application. But we're not looking at the Java applications. We're looking at the implementation of this application. Also look at JVM. So the JVM is multi-threaded. Even the Java application is not multi-threaded. This gives you a timeline view of your execution of the program. Each line represents a thread, and this gives you a call stack at a specific event. So this is the Java thread, the user thread. You will see what's going on here. And this is the thread that does garbage collection. You will see this is garbage collection happening here. This is the JIT, the thread that's doing the JIT compilations. So this tool just gives you a view that this tool does indeed support multi-threaded. It can look at the user level, or it can go into the JVM detail level. So we're talking about this, right? So user write code in a task level, and the OS provides threads. So a good performance tool should be aware of the threading model and provide relevant information. So if I'm writing OpenMP programs, I want to know my tasks. I also want to know the threading. The threading is OS support view, but I want to also know the task. So in this case, it can help you to identify the critical bottleneck easier. For example, in this case, it's OpenMP program. It gives you 3 metrics, different threads. So the first one is user CPU time. This is information provided by the OS. You look at this data, oh, it's almost all of them are around 80, 79. So looks balanced. So for the OS view, it looks balanced. But it is not balanced from the OpenMP view. Look at the work that for each OpenMP thread, there's huge difference. So why there's this difference? Why OMP work is not balanced, but OS work is balanced? Because the OpenMP needs a lot of synchronizations. And those synchronizations are implemented as P-threads. So the P-threads, the OS doesn't know whether it's OpenMP threads or P-threads. So the user CPU time only gives the view that OS has. So you have to look at these metrics, and the tool needs to understand OpenMP work to give you the information that's relevant to the programming model you have. So this gives you another view of the work. If you look at OpenMP work, there's a huge difference in the load. So the 10th challenge is recovery from errors. So it's very challenging. You want to catch errors and then restore the application to a stable state. So it becomes more difficult in multi-threaded applications because it becomes a synchronous problem. Usually, you can have an error, you can detect it, and you can restore it. But in this case, the error may be already propagated to another thread, and it becomes asynchronous problems. So you want to really deal with it, but a potential problem is that when the error fixing routine, you may run into deadlocks or infinite loops. So a common practice is to use a checkpoint. So when you design your program, if it's multi-threaded, you want to think in different ways when you do an error recovery. So the last challenge, is not least, is how to deal with single-thread errors, the errors in single-threaded issues. So you have these errors. They're not common. You're referencing an uninitialized variable. You have an out-of-bound array access, or you're dereferencing state pointers. So this has nothing to do with multi-threaded. They're just problems that in your single-thread applications. But it makes more difficult for you to debug that. There's all these traditional tools you can use, Lint, Purify, Vagrant, and the DBX RTC runtime error checking is a tool that's built into DBX debugger. It just becomes more difficult in multi-threaded environment. So you really want to have a good debugger to help you. So an empty, capable debugger. So you need to have these basic features. You need to be able to examine the thread status, to check thread-specific data, set breakpoints for a specific thread, and then control the execution of the threads. So you want one thread to run, the other thread just stay where they are, for example. You can have also some advanced features. You can integrate with deadlock or race detection tool. So when deadlock happens, the debugger will stop and give you the context, what's the problem. And you should be able to examine synchronization status. So it understands you're doing a locking, who is locked, all those things. And even better, you can understanding the threading models. So there are tools available there. DBX for Sun, TotalView for Atlas. GDB has certain level support for multi-threaded debugging. So here I use Sun's DBX as an example. So the first thing it can do is it print a list of all known threads. So in DBX, you say threads. So it lists, so for example, here we have 3 threads. Threads 1, thread 2, thread 3. And this column gives you the start routine for each thread. And what's the status right now? Is it running or is it at a breakpoint? And in which routine it is. And you also can switch to another thread to have a view. If you want to look at the call stacks, you can switch to another thread and check the call stacks, type where it will show you the call stacks for that particular thread. Or you can set a breakpoint for a specific thread. I want to stop at line 430 for thread 2. So I use this. So only when thread 2 at this line, the DBX will stop. So the breakpoint setting is synchronous. You just stop the whole word. So only when one thread when thread 2 reaches line 430, DBX will stop all the other threads. The benefits of this is that you can have a snapshot at that instance. So you can examine what's going on. Then once you find out what's going on, you want to resume your execution. So you can do several things. For example, you can say that a specific thread like T2, you should not run from this point. You just say suspend. In this way, thread 2 will not execute. All the other threads, if you say continue, all the other threads will continue execute. Then thread 2 will stop there. Or you can resume a specific thread. In this case, you can say, I say resume the previously suspended thread T3. Or you can T2. Or you can single step a particular thread. So you single step only this thread. All the other threads stay where they are. So so that's come to the conclusion part. So the multi-core architecture provides a thread-rich environment for us to use, for the programmers to use. but there's a lot of challenges. The challenges need to be addressed at all levels. Needs to be changed as language level, need to be addressed as compiler, tools level, as runtime library level, OS or virtual memory level, and we need to improve their programming practice. So my view is that in the next 5 years, there will be kind of chaos in the programming language community, trying to find out what's the best way to use the multi-core architectures. So every company is jumping and trying to figure out what's the right way. And all the programmers or the developers are just confused about this thing. And it's good for the companies to work together to figure out what's the right approach. So multi-core is becoming a mainstream. The fact that Microsoft even established a compiler team in Mountain View working on this thing is indication it's going mainstream. So not only HPC market, desktop, games, we'll see that. But until we have addressed all the challenges, the acceptance of the success and acceptance of multi-threaded programming will be limited. But even though that happens, we still need to working on that and make sure it happens, and make sure it happens successfully. So that's part of my tutorial. Do you have any questions? OK, please go to the speaker.
Tadao Nakamura, Kurchip's General Chair. In here, the granularity of threads is equal to that of tasks. You understand? Actually, my question would be the granularity of threads is equal to that of tasks. Yeah, usually in such a software problems, actually the definition of tasks and threads, very important.
Sorry, I didn't get your question. So
No.
you're asking the...
You have a mapping from tasks to threads.
Yes.
Of course, at the top of the stage, it's hard to hear the question because the acoustic problems.
OK, maybe we can take this offline and...
OK.
So I'll come to me after this part. Maybe we can talk offline.
Oh, that's OK. If so, another question, OK? You are probably, let me see, could you explain how the thread level parallelism is suited for multi-core architecture, for example?
So I guess the question is that try to explain why multi-threaded programming model is appropriate for multi-core architectures.
Right.
OK. So we don't know. It's one way to it's one way to use the multi-core architectures. So you don't have to go multi-threaded. You can make your program. You look at the programming logic. You may want to go multi-process, or you do want to go multi-core, or you don't care. So multi-threaded programming model just open a door for you, a way that you can leverage the hardware resource. Whether it's the best way to go, we don't know. It's been a common practice for a long time, and we're trying to improving it, and there are lots of challenges there. But whether multi-threaded programming will become the mainstream way to leverage the multi-core architecture, it's a question. I don't know, frankly speaking.
OK. OK, I understand.
So what the community and what companies are doing here is that it's a way to go there. We want to make it easier. We want to address all the problems. OK, next.
John Maschey, TechVisor. So one question that comes up, particularly to your first point there, is multiprocessors have been with us for years. Is there anything really fundamentally new in terms of the problems, other than the fact that we don't seem to be able to make single processors go much faster, so having multi-core means everybody has to deal with this? I mean, some of these problems have been around for at least 20 years.
You mean the challenge has been around for many
20 years, yeah, sure.
Yes, yes. So,
I mean, when you say a new thread-rich environment, you mean simply that lots more people are going to have to deal with it? Is that what you mean?
Yes.
Are there really new technical issues, do you think?
The technique has been advanced, and there's lots of reasons why we want to go multi-core, like the heat problems. So, in terms of the challenges is in writing multi-threaded applications, there's all the problems are there. It's just trying to make incremental improvements. I really want to see some innovative, revolutionary changes, but it's not happening right now. The fact that one interesting development is in the transactional memory, which the other speakers will talk. It's something new, and it opens more opportunities. So you can use that to do speculative parallelization, or you can introduce new languages. So so things changed. So what's changed is that the knowledge of the users, and maybe there's some new languages like Java. So it's a huge success, and the people spend tons of efforts try to provide concurrency utilities and define the memory model. It's something good. So it's incremental change. So next question.
Mohammed Ahmed, Qualcomm. In your section on debuggers, there's a bullet which says breaking is synchronous. Other threads should stop sympathetically. So in a real-time system, you can't always do that because, as you can imagine, you have one application running, and if you stop that application, you don't want to have other applications that stopped. Software programmers definitely do not like that, at least the ones I work with.
Okay.
So I wanted to hear your thoughts more on it and exactly what you mean by sympathetically.
Just that it stopped, and without you request one thread to stop, but the other thread just stopped. That's an interesting word to use. I cannot say anything more about it.
Sympathetic in Greek means sharing the pain. That's
Sorry.
Okay, I'm actually one of the speakers, but I wanted to address the question that one of the questions, which is, what is new about multi-core? Haven't these problems been around all the while with SMP systems? I think one of the things that's really new about multi-core is we are really trying to push this as mainstream computers. And when you're looking at SMP systems, these were really targeted at the niche market, which were mostly used by really sophisticated programmers. Whereas when we are doing this, you're trying to push this into every desktop and every laptop, and pretty much an average Joe programmer has to use this. The other thing that I wanted to also point out is multi-core actually, there are these challenges, but multi-core also brings in a lot of opportunities which are difficult to exploit, in the sense that when you looked at SMP machines, the different processors were like hundreds of cycles apart in communication latency and so on. If you look at multi-core machines, they are like 10 cycles apart. And so what this means is that in a multi-core setting, you are able to exploit fine-grained concurrency to a larger extent, much larger extent. Which means that if you're going to exploit fine-grained concurrency, then all of these issues that Yuan talked about, fine-grained concurrency, finding tasks, and so on, become much more pressing. And so while it's true that in some sense you can look upon multi-cores as SMP on a chip, it's also true that at a programming level, it's not really SMP on a chip. There are some unique issues in multi-core systems.
Thanks.
Hi, Mihailo Despotovic, Agilent Technologies. So back to the question of stopping the world. When you stop the world, you just see one instance of zillions and zillions possibilities. So I just want to hear your thoughts. Should I just run this hundreds of times and look statistically what's more likely to happen in the rest of the world when I stop it, or how do I approach that problem? So, I mean, you have 100 threads, you stop one thread, 99 of the threads stop sympathetically, but those 99 threads could be in God knows how many possibilities they can be, form the state of the whole world. So just how would you approach that? Statistic approach or how?
Yeah, it's a very, very challenging question. So what you really challenging problem that it's like you have a tool, right? This is one way for you to examine one state, but you really want to know what's going on overall the picture. So I don't know how to solve that problem. So what people usually do is that they will look at when they set a breakpoint, they have an intention in their mind. I want to look at. So when this thing happens, they have a snapshot of the world. So for the problem that you mentioned, you really want to know that what's the problem you want to solve. Maybe breakpoint is not the right way for you to find that information. So what is the thing you're looking for? And maybe you want to use different tools. Right? So it's difficult to answer this question if you don't have a specific task in your mind. If you want to really query what the program are doing, you don't need to set a breakpoint, right? You can have, like on Solaris, you can have pstack. They give you a snapshot of the call stack of all threads during the runtime. So you don't have to set a breakpoint in the debugger. So I'm not sure I'm answering your question, but it's a very difficult problem. Okay, so we'll take a rest and 15 minutes, and we'll come back for the next part of this tutorial.
I'm going to be giving an introduction to transactional memory, and then Christos Kozyrakis is going to come up and talk about implementation overview for transactional memory, as well as looking into hardware implementations of transactional memory. Then at the end of this tutorial, our session is going to talk about software implementation techniques for transactional memory. So as we were discussing towards the end of the last segment of this tutorial, multi-core architectures really change the way in which software developers have to develop applications. Software developers now really have to write parallel programs in order to take advantage of the power that multi-core architectures provide. Hardware architects are telling us that they no longer can give us more single-thread performance with each successive generation of chips. Instead, they're telling us they're going to give us more cores and perhaps more threads per core. So they've thrown the problem over the wall to us software guys. And now what we have to do is to take advantage of those extra cores and those extra threads on the core. We need to develop parallel programs to take advantage of them. So what this means for the average ISV programmer is that the programmer can no longer write a single-threaded application and then count on the next chip that's going to come out to give his customers better performance on his application. Instead, the software developer has to write a program that is parallel. And he has to write a program that is parallel and scalable so that once he deploys that application, when the new chip comes out with yet more cores provided, that program will actually be able to take advantage of those cores and to speed up. So this is really a fundamental shift in the way in which developers have to now develop programs. They now have to start thinking in parallel, and they have to write parallel programs. So this is really an inflection point in software development. Now, parallel programming is traditionally a very tough problem. And it's always been a problem for a very niche group of programmers. Now, though, it's coming into the mainstream, and a lot more programmers will have to deal with parallel programming. So our goal in the programming systems lab at Intel, where I work, is to look at new language constructs, new programming techniques that will help developers write parallel programs for these multi-core architectures, parallel programs that will scale once we provide more and more cores with each successive generation. Now, one of the most promising technologies that we've been looking at is transactional memory. So what is transactional memory? Transactional memory is a transaction on memory. That is, it's a sequence of memory operations that either execute completely, that is, they commit, or they have no effect at all, that is, they abort. Everything is rolled back. So a transaction is this all-or-nothing sequence of operations on memory. If that all-or-nothing sequence commits, then all the memory operations in that sequence will appear to take effect as a unit, all at once, on memory. However, if that sequence of operation aborts, then none of the stores in that sequence of operation will appear to take effect on memory. So that's atomicity. It's all or nothing. It's a one unit of operation, even though it's a sequence of memory operations. Now, transactions also run in isolation. They run as if there's no other thread in the system interfering with them. This means two things. One is that the stores that the transaction executes are not visible to anyone else, any other transaction in the system that may be running concurrently, until that transaction commits its effects. This also means that while one transaction is running, there's no other transaction that may be performing conflicting stores to memory. So transactions run in isolation. They run as if they own the processor, and there's no other thread in the world, no other transaction in the world that interferes with them. So this is a very nice construct for the programmer. It's a very nice mechanism, very nice capability, because it allows the programmer to think as if their transaction is executing serially. It's as if you're writing serial code. But in reality, of course, we want to allow concurrency in the system. So the implementation of the transactional memory system is going to allow as much concurrency as possible. But in terms of the abstraction provided to the programmer is thinking that this is a chunk of work that's going to execute atomically, and it's going to execute in isolation, and it's not going to have any interference from outside world. So this is a very nice abstraction. It allows the programmer to think that this is a unit of work that's executed as a unit, and its effect, it's like one single step within, even though it's running in a parallel environment. This is similar to database ACID properties, if you're familiar with databases, but it's different. For example, we don't provide durability guarantees. The effects of the transaction aren't persistent. Now, the best way to provide such an abstraction to the programmer is to provide extensions to the language, is to provide new constructs in the language. Let me illustrate this with an example. On the left-hand side, the programmer has written a piece of code that increments a shared variable x. So x is a global variable, and it's being accessed by multiple threads. And the programmer wants to increment that variable in a thread-safe way. So he really wants that increment of the variable to be done in a single step, even though there are other threads that may be accessing it. Now, to encode his intention of this increment being done atomically, he has to use locks using today's constructs. So he'll put a lock, he defines a new lock L, he locks that, he does the increment, and he unlocks L afterwards. So what does this do? This prevents all other threads that are executing this piece of code from executing concurrently. So even the programmer's intention was atomicity, he had to code it explicitly using locks and using synchronization. But with a language that provides transactional memory, instead, the programmer would write the code on the right. The language provides a new construct, atomic, let's say, and he simply puts the increment of an x inside of a block that is an atomic block. So this is much nicer because it's declarative. Instead of the user implementing atomicity using locks, he simply specifies his intent. I want this piece of code to be done atomically. And then it's up to the system to implement atomicity under the hood. So he's taken a lot of complexity out of the hands of the programmer and pushed it into the system. Now, this sort of atomic construct has been universally proposed. For example, there are new languages that have been defined as part of the DARPA High Productivity Computing Systems Initiative called Fortran, Extant, and Chapel. These are new languages that were built from the ground up to support parallelism. And these languages, instead of having locks, and instead of using synchronization in the way, for example, that Yuan showed in his talk, does away with locks completely. So there's no locks in these languages. Instead, they provide this kind of atomic statement. There's also been lots of research recently on taking existing languages, such as Java and C# and adding an atomic construct to it. There's also been research on taking languages, defining new languages, and defining them around the concept of transactions, such as the Atomos work done in Christos' group. Now, once you have such a construct in your language, you want to be able to implement these constructs very efficiently. There's a lot of responsibility now that's been delegated into the system. So there's been also a lot of research activity recently on what are some of the other constructs you can build around transactions. How do you do, for example, condition synchronization when you have a transaction construct rather than locks? Or how do you take an atomic construct and you compile it down for efficient execution on today's architectures? Or what type of new hardware constructs do you need to support such a construct? So transactions are a much better construct than locks. And let me illustrate that with an example. Here I'm showing you the hash map class from the Java class libraries. So the hash map is a very fundamental data structure in the class libraries. It's used by many applications. What the hash map does is, given a key object, it maps it to a value object. It's a very simple but very fundamental and powerful class in the class libraries. Now, the code I'm showing you here is the code for the get function. Given a key, get looks up that key in the hash map and returns the value. The code is a textbook implementation of a hash table. First, it takes the key object, it hashes it into an index, into a table, and we're implementing open hashing here, and then looks at that table entry, goes down a linked list, and finds an entry that maps that is equal to that key, and then returns the value mapped to that key, or returns null if no value is mapped to that key. So very straightforward textbook example. So the basic implementation of hash map in the Java 1.4 libraries is actually not thread safe. So you can't take this data structure and use it in a threaded, multi-threaded environment. The reason they did this was to not force the programmer to pay the overheads of locking if they don't need to use this library in a thread-safe environment. So if you wanted to use this data structure in a threaded environment, what you have to do in the Java class libraries is to wrap it with a synchronization layer. Java 1.4 provides this synchronization layer called the synchronized hash map that can convert any implementation of a map interface into a thread-safe variant. Here I'm showing you the code for get. It's the same method, but this one now is in a class that provides thread safety guarantees. The way it provides thread safety guarantees is via that synchronized statement. That is a lock construct. Given a lock mutex, which is a field in this class, it simply grabs a lock on that mutex. It then delegates that get call to an underlying map implementation that's stored away in some field M. And it does this same pattern for all the calls that are defined as part of the hash map data structure. So this is an example of coarse-grained locking. It's very easy to take something and make it thread safe using such coarse-grained locking techniques. You just take all your calls into a data structure library, and you protect them all with a single lock, with the same lock. So this is coarse-grained locking. It's easy to program this way, and it gives you thread safety. But the problem with this sort of coarse-grained locking is that it really limits your concurrency, and it leads to very poor scalability. If you consider this hash map example, if I have two threads, and they come in, and they want to look at the hash table concurrently, but they map the keys that they want to do an operation on map to two different table entries, even though that's safe to allow that operation to execute concurrently, this style of coarse-grained locking will preclude that kind of concurrency. Now let me illustrate this with a running system. Now what I have here is a 16-way machine that's running back at our lab at Intel. And what I'm going to show you here is the hash map data structure, first using a single thread. And we're going to be doing 500,000 operations on that hash map. And these are a combination of gets and puts and updates. So you see that we're making slow, steady progress on doing 500,000 operations. And it takes about 14 seconds to complete that 500,000 operations. Now let's do the same thing, but using the synchronized version. So now we have 16 threads in this racetrack. And what you'll see is now each thread is going to make progress one at a time. You get serialization. At the bottom here, you can see the CPU utilization. And if you look, and you probably can't see from the far, but what it shows you is that you only get 7% utilization. So we take that thread-safe version, but we're not going to get any concurrency at all. And in fact, it took 15 seconds because of the overhead due to locking. So coarse-grained locking is not going to give you very good scalability. Now, how would we write the same piece of code using transactions? Well, what you could do is just like where you have a synchronized layer, you could introduce a transactional layer where you take all the function calls, all the method calls that are part of that map interface, and instead of using a synchronized statement, you use an atomic, right? So here you no longer now have a lock object, so you don't need to declare a lock object, and you don't have locking. You just simply say, I want this get operation to execute atomically. Make it execute in a single step with respect to all of the threads, and make it execute as if it's an isolation. So as you can see, this is as easy as program as the previous example. I just erase the synchronized keyword and instead use atomic. So the ease of programmability here is the same as using coarse-grained lock. But the difference now is going to be scalability. So let me go back now to this system here. Now what we've done is we've built a research prototype where we've taken our runtime and we've introduced this atomic construct to the language. And we ran the same piece of code that I showed you with the hash map. Now what you're going to see is that all the threads are going to execute concurrently. They're going to make much more rapid progress than before, and you're going to get much better concurrency. So it's the same set of operations, same number of operations, but it executed much faster. In fact, it finished in 1.5 seconds. So we get much better concurrency and much better scalability using transactions compared to coarse-grained locks. So why did we get better scalability using transactions? Well, there's two reasons. With transactions, the underlying transactional memory system can keep track of all the memory accesses performed inside of a transaction. And it can provide you two forms of concurrency. One is it can allow concurrent read operations. if the system detects that two different transactions are concurrently reading the same location, then it's going to allow those two accesses to go ahead, because that is in general safe. Now, basic locks don't give you that kind of concurrency. Basic locks, simply the programmer says, you know what, let only one thread execute at a time. Now, there are fancier versions of locks that can be provided that allow the programmer to say, well, let two readers execute this critical section at a time, but don't allow any writers. But introducing a new form of lock simply makes the programmer's life a lot more difficult, because now he has to worry about yet another different type of lock, and he also has to worry about new forms of deadlocks and other kinds of problems that locks induce, but yet with a different kind of lock. When you use transactions, you get this automatically, essentially for free, because the implementation can provide it for you. Now, another way in which transactions provide scalability is by allowing two threads that access disjoint data elements to execute concurrently. In a multi-threaded program, in general, it's safe to allow two different threads to update two different locations concurrently, if those locations don't conflict, if they're not the same location. Now, again, you can get disjoint access concurrency using locks. But it's a lot more difficult, because now the programmer has to take their critical sections, they have to analyze what data is accessed by the critical section, and then break the lock into smaller locks that protect smaller pieces of data, and then take their big critical section and then break it up. Well, that's very difficult and error-prone to do in general. And it also introduces new bugs into your program. It has the risk of introducing new bugs into your program. It could introduce deadlocks, and it could introduce race conditions. And in general, it's not modular. You can't take a library that's been optimized to do this kind of fine-grained concurrency and expect to be able to compose that into a larger library or a larger piece of software that retains all the benefits of that tuning. And I'm going to illustrate that for you a little bit later. Transactions, on the other hand, provide this kind of disjoint access concurrency for free, because it's the underlying system that's going to track what you're reading and writing inside of your transaction and make sure that two different transactions always, that are running concurrently, always write different locations. So can I take the previous hash map data structure and rewrite it to get this kind of scalability using locks? Well, yes, you can. And this is what the code looks like. And in fact, in the Java 1.5 libraries, there's a new type of hash map called concurrent hash map. And here's what the get for that function looks like. As you can see, this is a lot more code. And in fact, this is not all of it. And if you analyze this code, what it's trying to do is it's trying to provide read concurrency, and it's trying to provide disjoint access concurrency. So that if two transactions update two different buckets in the table, they can execute concurrently. But the reasoning that goes into this is actually quite subtle. And this code was written by a threading expert, and it went through several years of review in the Java community to make sure that it's correct. Right? So you can do this with locks, but it's a lot more complicated, it's a lot more code, it requires subtle reasoning, and it risks introducing new kinds of concurrency bugs into the program, namely race conditions and deadlocks. So now we can go back to our system here and actually run this concurrent hash map. What you're going to see is you're going to get the same kind of concurrency as you got with the atomic. That is, you're going to see all the threads execute and make progress concurrently. And their execution time is going to be roughly the same, so about 1.5 seconds. So yes, you can get the same kind of concurrency with locks, but it takes a lot more work, and it risks introducing new bugs into your program. Now, this chart here takes that system that I demonstrated for you and shows you what kind of performance you get as you increase the number of threads, the execution time on doing a fixed set of operations on the hash map. And I show you 3 different lines here. One is coarse grain locking, which is the blue line at the top that goes straight across. And then I compare the fine grain concurrency, the concurrent hash map, with atomic. And I show you the execution time for 1, 2, 4, 8, and 16 threads. What you like to see, of course, is the time come down, because you're doing a fixed number of operations, as you increase the number of threads. And sure enough, what you see is that the atomic version executes as efficiently and scales as well as the highly tuned, hand-coded, fine-grained synchronization version. So you get scalability with transactions that is as good as the kind of scalability you can get with hand-tuned, fine-grained locks. So to summarize, what are the benefits of transactional memory? First, they're as easy to use as coarse-grained locks. So simply take your synchronized that you've put around your data structures and replace them with atomic. But you get scalability that is as good as the scalability as you'd get with fine-grained locking. But there's another benefit here too, which is composition. That is, you can take separately authored libraries that are thread safe and then compose them together in a manner that's still safe, that doesn't endanger introducing new deadlocks into your program, but get good scalability. Now, what do I mean by this? Let me illustrate this for you. Say I want to take that hash map data structure that I had, and I want to create a bank data structure, a bank class. And this bank class has methods for depositing into an account and taking money out of an account and transferring between two accounts. So what I need in this bank data structure is some data structure that maps from names of accounts to their balances. So a hash map seems like a very natural fit here, right? The keys are the names of the accounts, and the values are the amounts stored in each account. So what does a deposit code sequence look like? Well, it looks like this. I've got, first of all, in my bank data structure, I've got an account field, which is a map. It's a concurrent hash map because I want this to be thread safe, and I want to benefit from all the wonderful tuning that went into that concurrent hash map. The deposit takes the amount of the name. It looks up the current balance inside the map, given the name. It then increments the balance, and then it puts back the new balance into the same account. Now, the problem with this code is that it's not thread safe. There's a data race in this code. So even though underlying map structure that I'm using for accounts is thread safe, when I've composed it together to build a longer sequence of code, this code is not thread safe. So you can see where the data race happens. Here's an interleaving of threads that shows you the bug. Say I start off with $100 in Fred's account. Then I have two transactions that come in. Both of them deposit $10. One thread deposits $10 into Fred's account, and another deposits $20 in Fred's account. You can see here an interleaving of those two transactions, where the net result is $120. Even though I've got one $10 transaction and one $20 transaction, and the result should be $130, instead I end up with $120. And it's easy to see how this happens. The first transaction comes in. It does a get on Fred. It gets $100. It puts it into the local variable balance. Meanwhile, the second transaction comes in and does the same thing. He gets $100. The first transaction increments it by 10, while the second transaction increments it by 20. So the first transaction thinks the resulting balance is $110, whereas the second transaction thinks the resulting balance is $120. Now, they both do the puts. The put operations are thread safe, so one is going to be done before the other, right? The transactions are going to be, the locks are going to serialize these two activities. But the net result is going to be $120 if the second transaction goes second. So you lose $10. So you have a data race in this example. Now, the way to fix this data race is, of course, to introduce a new lock, right? So I take the sequence before, and I wrap that sequence in a synchronized statement. And I also introduce a lock. Here, I just reuse the accounts object as the lock. So now this is thread safe. But there's a problem. I lose all the scalability that I had in concurrent hash map. And now all the operations that go through my bank class have to be serialized. And if you think about this program, this problem of creating a bank data structure that is scalable, it requires you to actually redesign the data structures from scratch. You cannot simply take that concurrent hash map with all the tuning that went into it and reuse it to get scalability. You're going to have to redesign it from scratch so that you can use it in this new setting. So you lose composition altogether. Now let's take a look at this on our system. So I'm going to show you first the bank with one thread, and that's going to give us a baseline performance. And then I'm going to show you what happens when we run the synchronized version using 16 threads. So here we do about 500,000 operations. Actually, 1 million operations on the bank. So that took about 9.2 seconds. And now I'm going to use the synchronized bank with 16 threads. So this is the thread-safe version. Of course, it doesn't make sense to do 16 threads on the unsafe version. So here what you see is now each thread is going to take a turn, and you have serialization. So you have no parallelism at all in this version of the data structure. And what you're going to see now is it took 12 seconds. So you got to slow down here because of the overheads due to locks and the contention on those locks. How about the transactional version? Well, this is what the transactional version is going to look like. You, again, take the synchronized statement that you had. You took the coarse-grained locking version of your data structure, and instead of using locks, you use an atomic construct. But unlike the previous version, what you get here now is scalability. So let's take a look at the performance of this on our system. What you're going to see now is all the threads executing concurrently and a spike across all the processors. And a total time of 3 seconds. So you get a very nice speed up. So what happened here? We basically took the simple version of hash map. We wrote our code for doing a deposit completely in a serial way. Get the balance, increment it, put it back, serial operation, wrapped around an atomic, say, you know what, in a multi-threaded setting, I want this to be done atomically. So we composed things together, wrote a bigger data structure, but we got scalability. So transactions are as easy as coarse-grained locks. They scale as well as fine-grained locks, but they also give you this safe and scalable composition of separately authored data structures. But they give you another benefit too, which is failure atomicity. What failure atomicity means automatic recovery on errors. So if you have an error in your program and you want to recover from that error, transactions give you a nice mechanism to do that because it has this rollback capability. So you can use the natural rollback capability of the transactions to recover from errors and roll back to a consistent state. So let me show you that with an example. Let's go back to our bank example. Say now I want to create a new method on bank. And this new method does a money transfer from one account to another. So the transfer function takes two names, the names of two different accounts, and an amount, which is the amount to transfer from account 1 to account 2. So the way I would write this code is I would first, in this line, get the current balance from account 1, subtract the amount that I want transferred out of that, and then put it right back into the same account. So after this first line, the first account has been debited. And then I want to take the second account, get the current value of it, the current amount, increment it by how much I want credited, and put it right back. So after the second line, the second account has been credited. Oh, and by the way, I want the whole thing to be done atomically in a thread-safe way, right? Now, what happens, though, if there is an exception? What happens if one of these functions like get and put throws an exception? What if name, either one of the names is null? What if such an account doesn't exist in either one of those in the data structure? So what happens if an error happens during any execution of any of this code? What if an exception is raised? Well, I'm going to wrap this with a try and catch exceptions and explicitly handle the exception cases. But the problem here is when I'm in this catch clause, these catch clauses here, how do I know how much of this code was actually executed? How do I know which of the accounts may have been credited or debited? How do I know how to get back to a consistent state where no money has been lost? And how do I do this in a way such that other threads don't see an intermediate state that is not a consistent state? So I have to manually catch all the exceptions, figure out where I came from, which means put in code that sets flags and say, OK, now I did this, now I've done with that, I've already taken out of account 1, now I'm about to put into account 2, now I'm done with account 2. Then I have to check those flags in this exception handling clauses, and then based on what I have executed, try to roll back manually. And I also have to do this in a way where there's no uncaught exceptions. Because if there's an uncaught exception that propagates out of this try-catch, then the system will automatically release this lock. And now what happens is my data structures, my bank accounts, may be in an inconsistent state. I may have lost money in one of the accounts, and this is now visible to other threads, right? So I have to protect against all of that. So writing that kind of code is actually quite tricky. Using transactions, however, things are much simplified. Why? Because I replace the synchronizer with an atomic. If an exception propagates out of this atomic block, all the system has to do now is to roll back the state of the world back to where it was at the beginning of the atomic. It has to roll back the state of the bank and the accounts back to where it was on entry to the atomic. And since the transaction is executing in isolation, any partial updates that may have been done at the point where the transaction is raised are not visible to other threads. So this is very nice because it gives us automatic failure recovery using the transactions rollback capabilities. So as you can see, transactions are a very powerful language construct. And if we go back now to the set of challenges that Yuan showed in his slides, we can now begin to look at which of these challenges these transactions help with. Well, for one, you no longer, since you don't have locks, and instead you have atomic constructs, you don't have to define a synchronization protocol because you don't have synchronization. You don't have locks. So it completely eliminates that problem. Now, once you get rid of locks, you can get rid of deadlocks due to locks. So it helps us with deadlock avoidance. It eliminates the problems of deadlocks due to locks. As you saw, the transactional memory implementation provides us scalability automatically by giving us read concurrency and fine-grained disjoint access concurrency. So it helps us with scalability as well. Now, once you give automatic fine-grained concurrency and read sharing to the programmer, then the programmer doesn't have to try to go back into his program and break his critical sections into finer grains and introduce new locks, which can introduce race conditions. So it helps with race conditions also. But it doesn't alleviate that problem altogether because you still have to be careful that all your accesses to shared state are properly wrapped inside of a transaction and that you have the granularity of the transaction correctly. And finally, by giving us failure atomicity, this capability of rolling back on an error or an exception automatically, it also helps greatly with the problem of recovering from errors. So as you can see, transactions address a lot of the parallel programming problems that Yuan discussed. However, it's not a silver bullet. The programmer still has to think about his program and get things right. The programmer still has to try to find tasks that have to execute, that can execute concurrently, the programmer still has to map those tasks to the underlying threads. So the programmer still has to think. It's not a silver bullet for everything. And on top of that, transactions introduce or may make some of the challenges worse. For example, portable and predictable performance. The performance of transactions, since a lot of the functionality that before used to be done explicitly by the programmer, is now pushed and pushed into the system and delegated into the runtime. The performance of transactions, and therefore your program, now depends highly on the implementation of transactions. And as we're going to see later on in this tutorial, there's lots of different ways in which you can approach implementing transactions. So the performance of your application will depend on how transactions have been implemented on a particular platform. So to summarize and conclude this part of the tutorial, transactions provide many benefits over locks. They give you automatic, fine-grained, disjoint access concurrency. The system handles that for you automatically. They give you automatic read concurrency. So if two threads concurrently access the same location, but both of them are doing a read, the system automatically allows that. It avoids deadlock. The programmer doesn't have to use locks, and so he doesn't have to worry about deadlocks introduced by locks. It eliminates locking protocols. If you're not using locks, you don't have to worry about defining new protocols. And it gives you automatic failure recovery. If you have an exception, an on-caught exception, raised inside of your code, inside of your atomic statement, the transactional memory system will automatically roll back state to where it was before the transaction started. And so it recovers from errors very gracefully and keeps a consistent state in the world. So in summary, transactional memory are really a programmability feature. They're really a feature for the programmer, a feature that makes it easier for the programmer to write code, parallel code. It's a feature that allows the programmer to safely take independently authored thread-safe modules and compose them together into larger applications that are still thread-safe, but yet still scale very well. Now, we talked about in the beginning how this is a problem that was pushed onto us software guys from the hardware architects, this parallel programming problem. Well, I consider transactional memory now as a feature that pushes the problem right back to the hardware architects. So I consider this as the software architects strike back, which is saying, fine, we need to do parallel programming to get performance on these new multi-core architectures. But in order to allow mainstream developers to write robust, scalable code that can scale with each successive generation of multi-core processors, we need to have transactional memory. And to do that, we need some kind of hardware support. So the real challenge here for transactional memory is how can you implement transactions efficiently? What is the right combination of software and hardware to give you a system that provides transactional memory very efficiently and in a way that scales very well? So in the next session, we're going to talk about implementation techniques for transactional memory. That concludes my part of the tutorial, and I'll take questions at this point.
Two questions.
Yes.
One is, was the hash map example you showed running on your multiprocessor, I take it that had no hardware support?
That's no hardware support. That's basically a 16-way IBM X series machine with vanilla P4 Xeon machines.
So why do you need hardware support, number one? And I take it there are probably a lot of ugly things in an answer to that question you'll give. So what are some of the ugly things that you're going to see with transactional memory?
So I think your first question was, why do we need hardware support?
Yeah.
Well, I think actually the jury might still be out for that, right? We've been pushing the software technology as far as we can. And we've found that even with a software-only implementation and with compiler optimizations, you're still going to get slowdowns compared to using locks, because there's just a lot of overhead in the software system keeping track of all your read and write sets and doing validation of your read sets. So we suspect that you probably will need some kind of hardware acceleration. Now, whether it's a hardware giving you complete transactions or whether it's hardware support that allows you to speed up a software transactional memory system, that I think remains to be seen. Okay. And there may be other software algorithms. Maybe we haven't been smart enough with our software algorithms. Maybe there's other software algorithms that will significantly bring the overheads of a software-only transactional memory system down to reasonable levels. But at this point, given all the overheads that we've seen with the state of the software transactional memory research, we think that there's probably going to be need some kind of hardware support. Now, could you repeat the second part of your question?
The second part is that clearly things are not going to be as simple as parallelizing a
hash map,
trivially parallel piece of application. So where's the ugliness? You know, what you're hiding?
Yeah, so the example here was a very simple data structure. And we clearly need to look at larger applications and programming in the large, right? Because the way programmers will probably be using transactions is they'll be taking lots of libraries and gluing them together into larger applications and using transactions around, calls to many different libraries. So you probably will get very large transactions. So I think it's very important to make sure that your large transactions also scale very well. And we're doing some work to make sure that we can do that as well. So yes, this is a very simple example, and there's definitely challenges in making transactions work for very large transactions. And there's other things too, making sure that transactions work in the presence of other language features, in the presence of the runtime, garbage collection and exception handling, the presence of I/O. So there's still a lot of other challenges here as well.
Thank you.
I'm going to ask two questions, and I run the risk of just showing my ignorance. The first question is, based on the definition of the transactional memory requirements, my belief is that you have this implicit synchronization in that when you commit a transaction, there can be no other transaction in flight. Is that correct?
No, you can have other transactions in flight, and in the next two presentations, we're going to dive deeper into how you could allow concurrency and allow multiple transactions in flight.
So in your example is?
In the code that we were running on the 16-way? Yes, there were the 16, when you had the 16 processes running concurrently, they were all doing transactions at the same time.
But at the time that you commit a transaction, can there be
Yes.
Okay, so I misunderstood. And based on that, I don't have a second question.
Okay. Last question.
Could you show me the relation between transactions and the operating system?
The interaction between transactions and operating system?
Correct.
Right. So in the system that I showed, there turns out to be no interaction. But in general, they could be. For example, if you have I/O inside of your transaction, you may want to have the OS, some of the services provided by the OS to be transactional. For example, a file system.
Thank you.
Okay, thank you.
So hopefully by now you're convinced that transactional memory is a very useful construct that allows you to write simple code that scales well, performs very well if there is parallelism in your problem, right? So you cannot generate parallelism of thin air whether you have transaction or not. But if there is some there, then transaction allows you to exploit relatively easily. Some problem here? Okay, so now we're going to start talking about implementation. The thing that I want to point here is the following. If you're a programmer, all you need to know is what Ali talked about. So if you are a system vendor, your customers need to know all the previous stuff, and now we're starting to talk about what some engineers will have to know about in order to implement it. So this is the complexity that's going to be exposed only to the few, as opposed to everybody, as it is the case with multi-threaded programming. So there are two things that we have to worry about. We have to make sure that you can execute transactions in this atomic manner, all or nothing. and isolate it. Nobody sees intermediate side effects until you get the commit. So the easy way to do this is to actually run one transaction at a time. Okay, and it gets the right semantics, but unfortunately it also beats the purpose. The reason we reduce transactions in the first place is to get some parallelism there. So we're going to see techniques that allow you to get these two features without killing concurrency. So we're going to have to worry in every implementation about doing two things. One is allow for data versioning, and the second thing is to figure out when transactions have conflicts, when they operate with the same data, and somehow get to resolve these conflicts. Now, once you get down to the implementation, you can go multiple ways. You can do the whole thing in software as it was the case with the previous demo. No changes to the hardware whatsoever. You can also do most of it in hardware, which is called hardware transactional memory, and this is something that we've been working on for a while. And you can also do hybrid solutions, try to find the best of both worlds and throw only a little bit of hardware there and do most of the stuff in software so we have flexibility. Now, before we go into the specifics of hardware implementations or software implementations, we're going to talk about implementation approaches in the abstract. So once we get the main approaches there, then we're going to go into the specifics of hardware and software. So let's start with data versioning. The idea here is that at any point in time, as you're executing transactions, you may have multiple versions of exactly the same data. So you have one version of the data, which was the last committed one, the only node that you know to be correct at any point in time. And then every transaction can create another new version of that data. And until it's committed, it's speculative state. You're not really sure whether it's going to make it or not. So how do you handle all these multiple versions? There are two ways. The one way is called eager, and it's typically implemented with an undo log. And the basic idea is the following. The moment that you try to do a store in the middle of a transaction, before it commits, you update the regular memory location right away, okay? As if the transaction will commit at the end. Now, in order to make sure that you can recover the precise state of the machine, if the transaction doesn't commit, you also need to save the old value of that variable or memory location on the side. And you typically push it into an undo log. Now, as we'll see in a second, this approach allows you to do quite fast commits. But on the other hand, aborts are a little bit slower, and you may have some issues with fault tolerance and consistency of the system. Now, the alternative approach is called lazy, and it's typically based on a write buffer. And the idea is that if you do a store halfway through a transaction, you don't write it to the regular memory location. You put that new result on the side in a write buffer. Okay. And only if you actually commit a transaction, you will copy from the write buffer all the way to the memory location. As we'll see in a second, that makes aborts much faster and has some nice consistency features, but now it makes commits a little bit slower, and you may also have some extra redirection when you access data within a transaction in a software implementation. So let's use a small illustration here to understand what's going on. So we have some thread which is about to execute a transaction. It will operate on memory, and we have this one variable that has the initial value 10, and then somewhere on the side there is this structure and undo log. And it's hardware, software, something, doesn't really matter right now. Okay? So halfway through the transaction, you decide to update X to 15. The way that you do it here is the following. You actually update the regular memory location to 15, but before you do that, you make sure you read the old value and push it in the undo log. Now, if you're lucky enough that your transaction commits, then you're pretty much done. All you have to do is flash your undo log, and the regular memory location has already been updated. So your work is done. Flashing the undo log is quite simple. Now, if you're unlucky and your transaction needs to abort because it interacts in a safe manner with some other transaction that both operate on the same data, then you have to basically pick up the old value from the undo log, write it back to memory to restore the precise state of the machine. So, and that can be a little bit slower, okay, because you have to do some extra work. And now you can also see what's the problems with error tolerance and consistency. Halfway through your transaction, you have updated the memory location. So if your thread that's running the transaction crashes halfway, now you're left with this incorrect value in memory. And it will take some work to recover that, and actually if your crash affects the undo log, you may not be able to do it at all. Okay? It doesn't mean that you can never do it, but it's not an easy thing. Now, the alternative approach is lazy. And again, we have our thread, the memory, and some structure on the side, which we're going to use as a write buffer. So halfway through the transaction, we have this update of x to 15. And now we don't write the memory. We basically write on the side buffer the new value of 15. Now, what does this mean for future loads within the transaction? If you want to read something from this transaction, you need to check first the write buffer to see if the value is there, if the latest value is there. And only if the write buffer doesn't have the data you want, then you go to the memory. So you better implement the write buffer in a way that is very fast to search, because you're going to do that on every load. Okay? And of course, you can see that in software, this redirection can be expensive. So now what happens if you want to commit? Now you have to copy from the write buffer to the regular memory location. That can be a little bit slower. While aborts are much faster because all you have to do is forget the fact that you had the write buffer on the side. And now you can also see what's the consistency advantage here. You never really update the regular memory location unless you reach the commit point. So you don't have a long period of time where your machine is in this inconsistent state. And crashes cannot affect you that much. So this is what's happening with versioning. That allows us to start, abort, or commit a transaction. Now you also have to worry about dependencies between transactions. When two transactions run in parallel, if they touch disjoint data, everything is great. But every now and then they may touch the same variables. And we have to figure out when these dependencies occur and make sure that we execute things correctly and maintaining atomicity. So there are two things that we have to worry about. When you have one transaction reading and another transaction writing, and when you have two transactions writing the same data. The way that we do this is by tracking the read set and the write set for transactions. So we track everything they read, everything they write. We compare read sets and write sets, and we find dependencies. So again, there are two approaches. The one is called pessimistic. And the basic idea is that as you do these loads and stores, you do checks. If you find that there is dependency between two transactions, then you have to use some contention manager, some policy to decide what to do. You may abort one of the transactions. Some cases you can even stop. Now, the alternative approach is called optimistic or lazy or commit-based. And the idea here is that you run until the completion of one transaction. And when you reach the commit point, then you start doing comparisons and figure out if you overlapped in terms of read set and write set with any other transaction out there. And we're going to see in a second through some animations how they work. The thing I want to point out here is that you can actually use both of them. You can use one approach for loads and other approaches for stores if you want. You don't have to go just for one of the two. So let's go over a few cases to see how conflict detection works. And we're going to start with the pessimistic detection. So we have here one case where the transactions operate on disjoint data. So transactions 0 and 1, they start executing. And at some point, transaction 0 reads A. It's going to immediately check whether transaction 1 is touching the same variable. It's not the case here, so we can proceed. At some point, transaction 1 touches B. Again, there's a check. Negative again, so we can proceed, and so on. So at some point, the transactions reach the commit point. They know that they touch disjoint data. They can both complete, they execute fully in parallel. All is great with the world. Now, of course, life is not that beautiful all the time. And then in some cases, you have dependencies. So here, transaction 0 writes A, and transaction 1 reads it. So when you do this check here, you're going to realize that the read set of the one transaction overlaps with the write set of the other. So you have to do something about it. Okay. Now, you could abort and re-execute any one of the two. But because you caught the problem early, you can actually be smarter about it. So what you can do is, assuming that transaction 0 will finish quickly, just stall one for a while. Don't let that load return. So hopefully, this commit is going to happen soon. And you can install transaction 1, and it will do the right thing. It will seem as if transaction 1 executed fully after transaction 0. So with a little bit of a stall, you manage to execute these two almost in parallel. Now, you cannot always do that. In some cases, you have interruptions that require you to do an abort. So here you do read A and then write A. And let's assume that the policy that you use to resolve conflict says that the latest writer gets to win any competition. So since transaction 1 wins the competition, all you can do with transaction 0, since you've passed the point of reading, is basically say, I'm going to abort it, restart the whole work over again, And then hopefully the second time I do this read, transaction 1 is out of the way and I'm done. And then you also have to be careful about what policy you use to resolve conflicts, because if you don't use a smart one, you can end up with live logs. So here the two transactions are doing read, modify, write of the same address. So transaction 0 is reading and modifying, and the same with transaction 1. On this check here, you're going to catch the conflict, and let's suppose that you award the latest writer, which means that you're going to abort transaction 0. That's great. The problem is at the moment it starts, it's going to become the latest writer itself, so it's going to abort the transaction 1, and you're going to keep going back and forth without any forward progress. And of course, it's not a difficult thing to break. You just basically award the earliest writer. Okay? But you basically have to be careful about any policy you come up with, because it may have an issue under some scenario. So that's pessimistic detection. Let's say about optimistic detection, the same cases. So again, you have the two transactions. They execute the reads and writes, no checks whatsoever. Okay, you wait for one of them to reach the commit point. Then you do the check. You realize that there is no overlap, so transaction 1 can commit, and at some point later, transaction 0 will commit as well. Let's see the second case where we had some overlap, and with the pessimistic approach, we were able to stall. Here, we won't be that lucky. So we do all the execution, and when transaction 0 tries to commit, we realize that there's an overlap. So here, we will have to abort one of the two because we've gone past the point of reading and writing in both transactions. So we're going to have to abort, in this case, transaction 1. It doesn't make sense to abort transaction 0. It's already at its end. We might as well let it get out of the way. The second time you execute transaction 1, it's going to be the only one out there, and it's going to do the right thing. So with pessimistic conflict detection, we could not stall. We had to abort. With optimistic, I'm sorry. On the other hand, in case 3, we have it the other way around. When transaction 0 tries to commit, we catch the conflict. But in this case, we can commit transaction 0 without ever aborting transaction 1. If we do that, it will seem as if transaction 0 fully executed before transaction 1. So pessimistic conflict detection got an abort here, while optimistic basically finished successfully. And then another nice thing about the optimistic detection, I'm sorry again, is that it's much easier to provide forward progress guarantees when you catch the problem when transaction 1 is about to commit. You will abort transaction 0, but the nice thing is that when it re-executes, transaction 1 is out of the way, because we caught the problem when it was about to commit. So what are the trade-offs here? The pessimistic approach catches the problems, the conflicts early. So you can deal with some of the stalls in a smart way by stalling, and you can make sure that you don't abort too much work, but you may have some issue with forward progress guarantees. And it's exactly the opposite with the optimistic conflict detection. Now, if you take a look at the implementations out there, you will see that between the combinations of versioning and conflict detection, almost every single combination has been tried out. So there's no convergence right now. Now, will there be a convergence? It will depend on the following things. How do applications behave? How important are commits versus aborts? Then how successful are contention managers? How important it is to have a good consistency in your application and so on. And it may also be the case that it doesn't really matter. Okay, so whichever of these you do, it's fine. Or a different approach is better if you do a hardware-based one or a software-based transactional memory. Now, one interesting point is the granularity at which you track reads and writes and do conflict detection. You can do it at the object level, which makes sense from the programming point of view. And that's good from the point of view of overhead. You're going to do one check per object, and whatever metadata you keep around to keep track of reads and writes it will be at the object level, very coarse-grained. On the other hand, you may hurt concurrency and introduce unnecessary aborts. Imagine two threads which use transactions to operate in a big array, and the big array is one object. Okay, so even though you may be operating on disjoint parts of the arrays, you're going to see dependencies because of the coarse granularity of tracking. The other end of the spectrum, you have word granularity. You minimize these unnecessary aborts, but you're going to pay the overhead in time and space. And cache line granularity sits somewhere in the middle. Okay. And of course, you can mix and match, especially if you have a software system. You can do word-level granularity for arrays and object-level granularity for other types. Now, these are the main issues that you have to worry about transactional memory implementation. There are some more interesting issues that have already come up with a few questions. So you have to worry about how nested transactions work. Your code may call other code that includes transactions, and you have to deal with it somehow. The most common approach these days is subsuming. You have to worry about the atomicity of transactional code with respect to non-transactional code. And you have to worry about how do you support OS and programming language functionality, things like systems calls, like conditional synchronization and exceptions. And I won't go into the details, but a good reference is a paper by Austin McDonald at ISCA 2006. So I'm going to pause here for questions and give you a very quick overview of hardware transactional memory. So if there are any questions about the generic ideas behind the implementations, I'm going to take them now.
A quick question on relationship of this to classic database transaction stuff. You know, obviously there's some similarities and some differences. Can you talk a little bit? I mean, it seems like the big difference is the granularity that you're willing to do things at. Are there other ones, or you know?
Yeah. So granularity in general, you're going to see finer grained stuff. Plus, in database transactions, you're going to see basically people doing transactions over disks. I think the most fundamental granularity from the point of view of semantics is what Ali mentioned earlier, is that we're not talking about durability here. Talking about atomicity, consistency, isolation, but nothing about durability. The other thing which is interesting is from the point of view of a transactional manager, you can see everything as a resource. Your log-based file system is a transactional resource. Transactional memory is a transactional resource. You can bring everything together to have a transactional system overall, not just the memory or the disk or anything else.
Okay. Christos, you gave us the benefits and losses of eager versus lazy version management, conflict detection. Do you have an opinion on what you think will be the best or the winner?
I'm pushing a lot the lazy approaches and the optimistic, but again, I cannot prove right now that it's definitely going to be the one that wins the argument. So the thing with transactional memory is that we haven't done enough application studies to be 100% sure what matters. So we all have our arguments and so on, but nobody can give you an authoritative answer right now. It's definitely that. So to be fair here, everything is up for debate. And at the end, it may not even matter. Okay, who knows? Okay. So in the interest of time, we don't have that much of it. I'm going to go really quickly over hardware transactional memory. So why do we need hardware? Because software-only solutions can have a significant overhead. 40%, 2x, we've seen all of them. So you want to make sure you don't have to spend enough parallelism first just to break even with the sequential code. The other reason is that hardware transactional memory has some very interesting features. It works for, oops. I guess I went forward a couple of slides. It has some very interesting features. If you put transaction in the hardware, it applies to any code you write. So you can take your old code, your old libraries, and they work transactionally. You don't have to recompile everything. And you may argue that if I write a parallel program and properly compile, well, you will recompile your program, but not necessarily all the libraries out there. Now, how much hardware do we really need? We don't know. Okay, maybe we need a lot, maybe we need a little. The jury's still out. And the truth is that even the hardware-only proposals out there, they're really hybrid. They switch to software every now and then. So how do we implement transactional memory in hardware? Essentially do the following. We use the caches to keep track of the write buffer or the undo log and keep track of the read set and the write set. So the cache is the major mechanism that we use there. And that's great because that means that from the point of view of the processor, it does regular loads and stores, and behind its back, the caches do something smart to track everything. And in many cases, that can be zero overhead. You can apply this logic to private caches, shared caches, multiple level of caches, and so on. And then to detect when the conflicts happen, we're going to use the coherence protocol that's already there. All these multi-core chips exchange messages on loads and stores to make sure that the caches are consistent. So we're going to use exactly the same messages that we send around anyway to figure out when the read set of the one transaction overlaps with the write set of the other. Now, a few notes here. If you're familiar with thread-level speculation, the hardware is amazingly similar. And actually, there are many systems that do both transactional memory and thread-level speculation. And now in the back of your mind, you should also be thinking, wait, the caches are a limited resource. You cannot fit anything. Yes, that's true. I'm going to get to that in a second. So what do we do in the caches? For the most part, we annotate them to be able to keep track of read set and write set. So we introduce some bits that tell you whether a specific word is part of the read set and the write set. Here I'm showing word granularity, but you can do everything at the cache line granularity as well. So on a load, you set the read bit. On a store, you set the write bit. And of course, these bits you're going to have to flash at the boundaries of the transaction. Now, if you have an undo-based approach, you actually need to do 2 writes every time that you go to your cache, one for the new value and none to save the old value on the side. And of course, you have to do it once per unique address you touch within a transaction. Now, the detection basically uses this message that you send around the system. When you want to do a load for something that doesn't exist in the cache, you're going to request it in the shared mode, and you're going to look up all the other caches. If you request something in shared mode, and it exists in another cache with a W bit set, it means that you have a conflict. The one reads, the other one has written. And similarly, you can basically catch write-write conflicts. So I will quickly go over one example just to see how it works. We have here 2 transactions, one that copies the full object to the bar object, and one that just reads bar. And here it should be the case that either T1 executes before T2, so T2 should read the new value of the bar object, which is going to be 00, 97, or it's going to read the old value if it executes first, so it's going to be 00. And here I'm going to show a case where you use lazy versioning and optimistic detection. And you're going to see the same example with soft transactional memory later. So we start a transaction, T1, and we start basically reading and writing these objects here. So we're going to see them showing up in a cache. Some of them are part of the read set, and some of these are part of the write set. And we don't let the writes escape to the rest of the memory hierarchy because we have a lazy versioning system. So both transactions keep making progress, assuming that they're completely independent. And now transaction 2 also pulls stuff in its cache and marks them as part of the read set and the write set. So for some reason in this example, T1 runs faster. So it basically finishes the second statement and it's ready to commit. So what happens then? 2 things. First, you update the main memory. So you take the stuff that you had written in your cache and you make them available to the rest of the system. You can do this as an actual copy or just as a logical copy. This is valid data sitting in the cache 1 as dirty. No copying explicitly done. Now, as you do that, you also need to clear basically the read set and the write set. But most important, you also need to communicate your write set to the other caches by doing this exclusive request, which you would do anyway whenever you write data. So cache 2 is going to be notified that cache 1 wants to write exclusively these 2 variables. One of the 2 sits in its cache, and it's part of the read set of the execute transaction. So there's your conflict. And it makes sense to let this one finish and then roll back this transaction. So we're going to detect the conflict, roll it back, and re-execute it. And we can do exactly the same scenario with all the other combinations. Now I have a long discussion in the slides about how we've done this thing for more complicated applications like SpecJBB. I won't spend much time going over it. The main thing to take here is the following. We're able basically to take SpecJBB, which is a 3-tier benchmark, change 2 lines of code to basically enclose a big operation like ordering something new in a big transaction, and then in a simulated hardware transactional memory system, get the speed up of about 2x. So big program touches many bit trees, pointer-based data structures, who knows what's going on there. You add 2 lines of code and magically 2x. And actually, if you are a little bit more careful and go and use nested transactions, which takes the new line count to 4 to 6, you can get about 4x performance. And as you can see here, this is execution time, so lower is better with 100% being the sequential. You actually spend a significant amount of time working on both transactions. This is not programs that have no dependency whatsoever. Dependencies happen, and they happen often. But you take care of them behind the user's back. The user has all need to say, take this thing, execute in parallel with everything else, but make it atomic. So there's this issue of limited resource in the caches, and you have to somehow virtualize them. The caches may overflow, and you may take an exception halfway through a transaction. So you have to worry about that. There are a couple of approaches. The one is to use some hybrid implementations. So you start with hardware transactional memory, and if you run into trouble, you switch to software. And the main thing that you have to worry about is how do you detect conflicts between hardware and software transactions. And there are smart ways to do this. One of them is highlighted this here at ASPER 2006 in a paper by Saha. The other way to do this, basically, is by mapping key structures of the hardware transactional memory in the virtual memory system. That was pioneered by a paper by Intel at last year's ISCA, where they took the write set, the read set, and the write buffer. They say they all belong in virtual memory, so they're infinite. And we just cached the working set in the processor caches. Okay? So they did this using hardware and firmware, and in a recent paper, we did exactly the same thing by using the operating system. So instead of adding hardware and firmware, we said the operating system can already give you transactional memory at the page granularity. And that's not that good, but as long as your backup mechanism and not the main one, then it performs quite well. And it also turns out that you can be a little bit smart about how to deal with transactions, with interrupts in the middle of transactions. You should not always virtualize. Sometimes it's better to just kill the transaction and restart it later. So I'm going to skip the rest of the discussion in the rest of time. So I'm going to pause here and take a couple of questions, and then we can switch to software transactional memory. Now, one quick note while people stand up is that the slides here are slightly modified from the handout. The main message is still the same, and all the slides will eventually show up on the HotChips webpage, so you can get the latest version as well. Any questions? Can you go to the microphone, please? They videotape the whole thing. So.
Is there anyone actually making hardware transactional memories?
You mean processor vendors?
Actual processors.
So that I don't know, and I think it's going to take. So I don't work for any of these companies. Actually, whenever you have an academic talking about implementations, you can tell it's the early stages, right? So just to be clear about that. So many companies are flirting with the idea now. When it so Intel for sure is looking at this thing. Now, what exactly, how much hardware they're going to throw into transactional memory? It's up for debate. And it's, for example, easier to think about cases where you could do a software transactional memory, you will profile it, you will come up with the 2-3 instructions you need and do those, as opposed to do more in hardware. But the jury is still out. Here at Stanford, we have an FPGA-based prototype of an 8-way PowerPC system running transactional memory Linux that works, but it's still too early to say who's going to do it and in exactly what form.
Thank you.
Tommy Thorne, Transmeta Corporation. You were going a little bit fast, so I didn't quite catch when the cache communicates to the other cache that is done with a transaction. Is that an atomic operation?
No, it doesn't have to be atomic. You mean the messages that you send, basically, these are the regular coherence messages. So there are some ordering issues and so on, which is whatever you had to do for coherence to begin with. You just basically add to that the fact that they're also performing checks. Now, some systems, and this is definitely the case of one of the systems that we built, allow you to commit one transaction of the time. Okay, so you don't serialize the computation, you serialize the commit. Even in those systems, you can go and do two-phase commit and parallelize everything. But you don't really have to have all the communication be atomic. There's something that has to be atomic, but it's typically much finer granularity.
Is this mic? Yeah, it's working, right? Yeah. Okay, thank you, Christos. So I'll conclude this part. So I'll conclude this part of the tutorial by focusing on software transactional memory. And there are really many reasons for why you want to have a very robust and very high-performance software transactional memory. And really, one of the main issues there is as you go and pick at all of the details of transactional memory, and then you figure out all the hardware that needs to be added to really handle all of the corner cases, you end up with a huge laundry list. And invariably, all of the current proposals for virtualization end up with some kind of a software overflow mechanism or some kind of fallback on software, which is why you really need a very high performance software system to make sure this doesn't become a bottleneck. Okay. So what I'll be talking about is, and Ali talked about this in the first part, which is here you have an atomic language construct. So it's sort of the programmer throws this construct over to the language and the runtime system. How does the language and the runtime system deal with this? And if I have time at the end, I'll touch briefly on hybrid transactional memory, which is, you do some things in hardware, and then how do you gracefully, or, how do you sort of revert to software when things get too tough for the hardware? Okay, so let's start with this atomic construct. And so you have this, the programmer puts in this atomic construct, and then he has, these things inside of a shared region. And essentially, the first thing that needs to happen is that the compiler needs to go and tell the runtime system, well, this is where the transaction region begins. So, the compiler sort of adds this function, a call into the transaction memory library, that says, well, this is where the transaction memory region is going to start, so let's initialize all the internal data structures so that we can do the conflict checking and so on. And then when you get to the end of the transaction region, you have another call to a runtime function that says, well, now we need to commit all of the speculative updates that we have made inside of the transaction region. And then now what needs to happen is that each of these shared memory accesses, and in general these are variables that the compiler cannot prove are thread local, have to get instrumented, so that you can keep metadata on the side that detects all of the conflicts. So in this particular example, that this read of A gets converted into some kind of a code that says let's instrument this, and the same thing happens with the write into this shared variable, right? And the point is that all of this instrumentation gets done automatically by the compiler. So as a programmer, you really are writing this construct, and then the compiler is adding all of this stuff. So how does then, we have added all of these codes and we have all of these instrumentation functions. How does the runtime now maintain all of the metadata that is needed to make sure that we provide the properties of atomicity and isolation? Now, essentially, if you look at all of the STM structures, you can sort of abstract it down to a set of very fundamental data structures. And these are essentially, some of these are per thread data structures, and some of these are per data metadata. And so for the per thread one, what we have is something that we call a transaction descriptor. And essentially, it maintains all of the transaction-related metadata for that thread. So, these are the variables we have read, these are the variables we have written, and so on. And there's something else that we maintain that, I'm calling a transaction memento. And essentially, this word memento comes from design patterns. And what this is really used for is being able to do nested transactions. So, you have one transaction nested inside another one, you want to be able to do a partial rollback, and that's when we use these mementos. Not something that I'm going to talk about in the rest of this presentation. And then finally, there's a per data metadata. This is sort of acts like a metadata that controls access to the data. And I'll talk more about this and give examples of more about this. And essentially what this acts as is it sort of controls access to all of the data it protects. And it can essentially be in one of two states. So if you want to think about it, you can almost visualize it as we use these per data metadata or these transaction records to emulate some kind of a coherency mechanism in software. So this transaction record can be in one of two states. It can either be an exclusive state, which means only one particular thread can read or write that particular data, or it can be in shared state, which means everyone is allowed to read that particular data. Now, how do we map data to transaction records? Because the point here is every piece of data that could be accessed by a program somehow needs to get associated with this guard that protects access to this data. Now, if you have a managed language, such as Java or C#, then what we do is add an extra word here to the object layer, right? So in some sense now, this transaction record here guards access to all of the fields in this particular object. Now, if you have an unmanaged language such as C or C++, you could end up with arbitrary pointers inside an object. So essentially, given an arbitrary pointer, there's no way you can figure out where the object is starting. And what we do in that case is use an address-based hashing. So at runtime, the transaction memory library maintains a table of transaction records. And so given any particular address, we use the address to hash into this particular table of records. And now you can see that depending on the hashing function, I can get any granularity of conflict detection. So for example, if I take the address and I mask out the lower 6 bits or whatever is the cache line size, then that gives me conflict-based detection because all of the addresses in one particular cache line are going to get mapped to the same transaction record. Now, I'll go through an example of how we use this in our runtime, and this is actually very close to the runtime that, to the demo that Ali gave, and this is sort of diving down into the details of how we implement this. So what we'll do is use classic two-phase locking from databases, but we'll have a twist to it which says, we'll do classic two-phase locking only for writes, but we'll use an optimistic concurrency for reads. So we'll use versioning for reads, and this is really important to get good performance. So we come back to the same example that Christos talked about. So we have these two objects here, a foo object and a bar object. And they have this normal object header, but they're now augmented with these transaction records. And now one way to actually quickly check whether a transaction record is in a shared state or in an exclusive state is by looking at the bit pattern. So for example, what we do is say, well, if the value there is an odd number, then it's in shared state, which means everyone is allowed to read it, which is why they start off being in shared state. So this is one transaction that's taking the foo object and copying it into the bar object. And this is the other transaction that is reading the fields of the bar object. And because we have to guarantee atomicity and we have to guarantee that the whole thing executes in isolation, what this means is that T2 should execute as if it executed before the transaction T1 started or as if it executed after the transaction T1 ended. In other words, it should either read the value 0, 0, which is before the transaction T1 executed, or it should read the value 9, 7, which is after T1 got committed. You should never see any interleavings of values. So the way it now works is, let's say the transaction T1 starts, and then it reads this foo object. Now note that this particular read, as I showed in the example before, has been instrumented. So you have put in some instrumentation function there so that you can maintain some data on the side. And what that is going to do is remember here that in the transactions data structures that we have read the object foo, and the version number of that object was 3 at the time we read it. And then the next transaction starts, and then it says, well, I have read the object bar, and then you remember that this had version number 5 when you actually read the object. So in some sense, these version numbers are timestamps. They say this was the time, in some sense, at which this object was last modified. And then you come along, and then this transaction T1 proceeds, and now it wants to do a write into this bar object. And what we'll do here is use locking, strict two-phase locking. So when we actually get down to doing the write, we are going to go in and take ownership of this object. So this tells the rest of the world that transaction T1 is in the midst of modifying this particular object. And when that happens, we'll go and do an in-place update. So this is using eager versioning. We'll go and do an in-place update of this particular object, but at the same time, we maintain in the data structures here that the previous value was 0. And we also remember the fact that we actually acquired an exclusive access on the object bar. And then this goes on, so the transaction T2 comes in and it finds that this object has been locked, so it waits because it doesn't want to read a speculative value. And then foo comes along, it again reads the object. The transaction T1 comes along, again reads the object foo, again notes the fact that it has read the object foo with a particular version number, goes along, does an update into bar, and again it does an in-place update over in here and remembers the old value that it has in its log set. And now it gets the end of its transaction. So what it now needs to do is make sure that, so if you notice here in the reads, we kind of optimistically assume that no one is going to conflict against us. So we just go ahead, just maintaining some metadata, assuming no one is going to come sneak in behind our back and change any of the data. But before we actually get to committing it, we have to make sure that this optimistic assumption was indeed valid. And this is what we call validation. So at this point of time, The transaction comes in and checks the version number of all of the objects. And then it goes to the read set and sees that both of the objects, the version numbers haven't changed, and then it knows it can actually go ahead and commit it. And when it goes and commits, what it does is it releases the lock on this object. But one of the things it also does when it releases the lock is increment the version number. Essentially, it says there is a newer version of the object, so if someone had read a stale value, they know that when they actually get to the validation. And then you just get rid of the metadata. Transaction T2 wakes up now. It's been waiting for the object to be released. It comes to the commit point. It goes through its validation. It sees that the validation fails, and it aborts. And restarts and so on. And of course, because this is all a software mechanism, you can use a variety of contention management policies and do a number of fancy things, but I'll sort of defer that. So this was one particular implementation, but clearly, and Christos also alluded to this, there are a number of different ways you could implement this. So for example, in this particular example, we used optimistic concurrency. So this was essentially saying, well, let's do versioning on the object. But you could, when you did actually a read, go ahead and grab a lock, grab a reader lock on that particular object. And the problem with that is that when you actually grab a lock on a particular object when you're doing a read, you're essentially converting a read into a write, which means you end up with very poor caching effects, because that object is going to keep bouncing between all the different caches. And the other thing is that you actually end up doing a lot of lock operations, so that adds to the overhead. And we did a very detailed quantitative analysis of this, which is available in a paper last year. Now, the same thing could happen with writes, and in this case, we were using a pessimistic write, so we actually went in and grabbed the write lock and did an in-place update. But you could do this separate thing, which is buffer all of the writes on the side, and only when you get to the end of the transaction, actually go and do the in-place and do the updates. And then there are again these trade-offs. So if you actually do an in-place update, then you get very fast commits, because when you get to the end of your transaction, you're pretty much done. But if you do the other way around, then you have to copy things over at a commit. And then the other thing that happens is if you buffer updates on the side, and this is also something Christos alluded to, when you actually do a subsequent read, you have to search for what is the latest value, and that slows down your critical path. And again, we did some quantitative studies about this to see what works out best. Okay, so this is as far as the transactional memory library is concerned. Now, what you also have to build in addition is a lot of support in the virtual machine as well as in the compiler. So one of the things you need to do is version the function. So because if you're inside of a transaction, you need to instrument your reads and writes. We need to have a version of the function that is transactional, that you're going to call from inside of an atomic block, and then a version that you call in general when you're outside of an atomic block. And I'll touch a little bit about later on in the slides about a good compiler representation. One of the things is, since we are inserting so many runtime calls, you need to be able to do a really good job of doing a CSE on those and doing some very aggressive inlining. And finally is, in a managed environment, all of the state that you're maintaining on the side needs to be visible to the garbage collector. So because a transaction could be interrupted at any point of time, and you need to make sure that all of your state gets enumerated to the GC. And so the details of all of this are actually there in a paper we published this year in PLDI. Okay, so just to touch briefly on the compiler optimizations, again, we take the atomic block and we instrument all of the reads and writes. So this a.x becomes a call to this function and doing an STM write of a.x. You're going to write into a.y. This again becomes an STM write into a.y and so on. Now, one of the things that you want to notice here is that there's a lot of redundancy here. So if you notice these two STM writes, they would actually try to grab the lock on the same object and then do the undo logging. But that is really redundant. Once you have grabbed the lock at this point, you really don't need to grab the lock at this point. And moreover, when you do the read of the same object, you already got exclusive access of it. So there's no need to check whether this object is free for reading or not. But all of those, redundancies get hidden if you use these high-level primitives. So the next thing we did is actually implement, lower down this representation in the compiler IR and expose these redundancies to the compiler. So for example, this write barrier gets broken up into these two functions. One of them says, go take ownership of the object. The other says, go do the undo logging for the object. And now when you do this, then these operations become redundant. And so you can use classic CSE to actually get rid of all of these redundant optimizations. And then when we do this, we really end up with code that's much more efficient than what we started with. And in our compiler, we do a lot of other traditional optimization. So for example, we'll do things like, well, if a particular field or a particular class is immutable, then you don't really need to do any undo logging because no one else is going to write into it. And then we also detect whether some particular object is thread local or transaction local. And in that particular case, you again don't need to do any instrumentations. And of course, the last one, which is really important, which is you want to inline all of the fast paths to get good performance. Now, when you add up all of those, you actually end up with a pretty high performance software transaction memory system running all by itself without any hardware support. So this is, if you start off with the base STM, the blue one here is the locking code. Okay, so this is the thing that we are trying to compete against when it comes to single thread performance. And if you look at the just the basic STM without throwing in any of the compiler optimizations, then you could end up with about 80% extra overhead or 70 to 80% extra overhead. But then once we add in all of these optimizations, so doing redundancy elimination over here, then detecting whether one particular object is immutable. If that's the case, you just get rid of any objects. And then finally doing the fast path inlining, then this overhead comes down substantially. So essentially, you can bring this down to about a 30 to 40% overhead over the sequential code, or about 10%, 20 to 30% overhead over the locking code. And this is on a single thread. So as you then scale this up to multiprocessor, you're going to get back the scalability advantage from it. Okay, so that's the software TM part of it, but even if you throw all the compiler optimizations at it, you still end up with 30 to 40% overhead. And if we want to sort of deploy something like this, one of the common things we hear from ISVs is, well, we don't want it to slow down our code, even though you give us all of these really nice properties. And so one of the things that has been proposed, and there's been a lot of ongoing work on this, is can we use hybrid transaction memory? So if a transaction is small and it's simple and there's no complications, you won't have garbage collection inside and there won't be context switches inside, there's no nesting and so on. So the really small, simple cases, we are going to handle those using a hybrid transactional memory. And if that comes along something that we can't handle in the hardware, then is there some way we can fall back on the software transaction memory? So the thing about this is, once you have this concurrent execution, you can have a hardware transaction executing and a software transaction executing concurrently. You now need to make sure there's proper conflict detection between the two. So if you have concurrent STMs, two concurrent software transactions, then the STM machinery is going to take care of that. And if you have two concurrent hardware transactions, then the cache coherency mechanism takes care of that. But the problem is you may have a concurrent HTM and an STM transaction going on. And the way it is usually handled is you say, well, we're going to add up a little bit of code in the hardware transaction so that a concurrent software transaction is aware of the fact that a hardware transaction is running, and we can get the right things done. So the gist, due to time, I'll just present the gist of the idea. But what happens in here is when you're doing an HTM transaction, you essentially go in and check the transaction record for that particular object or that particular data. And then what you see is you check whether it's been locked by a software transaction or not. And the idea is if there is a concurrent software transaction running, you don't want the hardware transaction to proceed because this transaction could have been context switched out. So a cache coherency mechanism isn't going to help you detect conflicts. But if there is no software transaction currently active on that particular object or that particular word, then you go ahead and do the transactional operation. And the reason it's safe is that if a software transaction subsequently tries to access this object, to mutate this object, it's going to abort the hardware transaction, simply because the object is now in our read set. And the same thing happens for a write. So you first check that there is not a concurrent software transaction running. And if there is nothing running, then you actually perform the transactional write, but you also increment the version number. And essentially, what this is saying is you increment or you do the mechanism that the software transaction uses for detecting conflicts. So in the example that I used, it was, well, when you increment a version number, another software transaction knows that it needs to abort. The hardware transaction does the same thing. And so the nice thing about this is that if you are running in as a hardware transaction, then you can get rid of some of the software overhead. So in the example I showed before, you had to maintain these read sets and write sets. In this particular example, you don't have to maintain those sets while you're running as a hardware transaction. Okay, so to conclude, there has been a lot of work in transaction memory over the last 2 to 3 years, but clearly there's a lot of additional work that needs to get done. And one of the things is what I mentioned at the end, which is how do you find the right combination of hardware and software support to get really good performance. And the other thing is, when you have these hardware, when you have these transaction mechanisms, and Christos also showed a slide about that, you can end up spending a lot of time in aborted transactions. And so we need a lot of good diagnostics tools, and this is also something Yuan talked about in his talk, that really tells the programmer, these are the hotspots in your transactions, these are the data items that are the objects of contention, so that they can actually go in and fix these performance issues. The other thing that needs to happen is integrating transactions as a language construct. So for example, if you're using it as a programming construct, you have I/O inside there, and then you're going to have nested transactions, and then you'll have threads, right? So for example, let's say we have started a transaction, and then we spawn threads inside a transaction. What is the semantics of that? Do you actually detect conflicts between threads inside a transaction or not? So there are a lot of these open semantic issues that still remain as we try to integrate transactions within a programming semantics. And then finally, there's the system integration issues. So if you're doing interacting with the OS, if you want to have debugging support, if you're doing RPC and so on, we still need to figure those issues out. Okay, so it's clear that with the multi-core processors being aggressively pushed by almost all the hardware vendors, we are at an inflection point as far as software development is concerned. And as someone put it, I think it was there in that paper, in the concurrency revolution paper, much of the free lunch for software is over. And so what all this means is that we really need new programming abstractions. And in some sense, if you look at locks, locks are sort of the assembly language for doing concurrency control. And what we're trying to do with transactions here is say, well, we want to raise the level of abstraction so that the programmer doesn't really have to deal with locks. It comes in and just says, declaratively, this is an atomic block of code, and delegates to the runtime and the compiler system and the hardware how this entire transaction machinery gets implemented. So, finally, there's been a lot of good research on implementation and on semantics issues, but clearly there's a lot more work to be done as well. So with that, if you have any questions, I'll take those now.
Yeah, in the example, you show one version number for 2 variables, right? Now, in the previous example, with the hashes, you had a lot of variables, or let's say there were 2 arrays. Mm-hmm. would you end up with an array of version numbers? Or would you just, what level of granularity do you want to work at on the software?
So are you referring to this one?
Yeah, in the example, you have X and Y there.
Yeah.
Right, and you have one version number.
Yeah.
Right, so let's say X and Y were arrays and there was a dynamic index in there.
Uh-huh.
So would you then have an array of version numbers?
You would, in the runtime system, essentially you would also have, for doing things like arrays, we actually have a table of, and that's the thing that I was referring to here, is you actually have a table of what we call transaction records. And essentially you use an address-based hashing to go and index into this table of transaction records, yes.
Can you give us some context, sort of talk about the different kinds of mainstream applications? If I look ahead 5 years, 10 years, which things do you think will be using this? Will Word have this?
Yeah, so we have, what we have seen, so one of the things about transactional programming is we haven't really taken a lot of, real-world applications and done this. But I would think more of the server-side applications is what would see a lot of use of this. So things like MySQL, Apache, and so on is what would see more use for this.
Looking at this from a hardware manufacturer point of view, isn't this a scary prospect, this hybrid business? The fact that your hardware would have to rely on this software out there to get the job done?
It turns out that, if you look at the alternative, which is do all of it in hardware, it might turn out to be scarier.
Maybe, but, this is a kind of hybrid approach. Typically, hardware has done the job itself, just so the manufacturer could have some kind of control over the situation.
So that's not necessarily the case. If you look at virtual memory, you have the DTLB. If you miss in it, you do a page walk. Now you may have a hardware page walk, but you still have the operating system do it in software. Yeah. So it is the case that there is no good answer for what is the right amount of hardware support. And another example is register allocation. You just have 6 registers. You have the software actually virtualize those registers.
Right. But in the answer to both of those things you mentioned, the hardware engineer has this easy fallback. He says, my mechanism is correct. How you use it is a software problem. Your problem, not mine. But now you have down in the basic mechanism of the loads and the stores, this big software system out there.
Yeah, there's a big software system out there that essentially is using the underlying hardware mechanism to speed up some parts of the program.
Yep.
So yes, there is a reliance on the software system to get it right. But again, it's not yet clear now what is the right amount of hardware to put in, and what is the boundary? How do you delegate things to the software and to the hardware? And that is an topic of a lot of research now.
Maybe you covered this and I just missed it, but with the lazy stores, if part of the problem is slow commit times, could you not just change where the memory address is pointing to your write buffer rather than copying into the original memory location?
That would be difficult, right? Because you'd have to go in and rewrite your program. Are you saying you would do this in the hardware, or do you want to do this in the software?
Well, I was thinking with virtual memory, you talked about how it was being used with virtual memory. Could it not just change where the virtual memory pointed to?
You would, conceivably, you could say, well, so the first thing is you would then have to do things at the page granularity, which would, basically make it really coarse-grained. But let's assume for the time being you wanted to do something at the page granularity. You could do it and conceivably go in and change your page table mapping so that you make them point to an alias location. But anytime you sort of say, let's do it at the virtual memory level, involve the OS, then the whole thing becomes even more inefficient.
Okay, thanks.